So here's the famous Grand Canyon in Arizona, a gigantic crack in the ground of incredible beauty and grandeur. Now, imagine it dozens of miles longer and lying at the bottom of the ocean. In fact, you don't have to imagine it, because you can see this scene in real life. A massive crack in the ocean floor lies about 620 miles west of Portugal. This mysterious rift is called the King's Trough Complex. It's a broad system of parallel trenches and basins descending into the dark depths of the Earth's crust. All of this awe-inspiring beauty stretches for about 310 miles. The deepest part of the system is known as Peak Deep. It's located at the eastern end and is one of the deepest places in the Atlantic Ocean. The Bermuda Triangle, the Mariana Trench, and other places, surrounded by mysteries, secrets, and legends, may fade into the background compared to the King's Trough Complex. There are no frightening stories or records of vanished ships here, but just imagine it. At the bottom of the Atlantic Ocean, in icy waters where almost no light reaches, lies a giant unexplored rift. What's down there? What kind of creatures might be found? Perhaps there are remains of sunken ships. We are unlikely to find out anytime soon because reaching it is extremely difficult due to the immense pressure. For now, the only thing scientists truly understand is the origin of this underwater canyon. But first, let's look at how similar formations appear on the surface. The Grand Canyon, for example, was formed by a river. Meandering slowly over millions of years, it carved through the region, washing away and grinding down sedimentary rock. So here's the question. Do you think something similar happened to the floor of the Atlantic? Of course, there are no rivers there, but what about underwater currents? Could they have created such a giant, dark fissure reaching deep into the Earth's crust? Well, in fact, no. The origin of the King's Trough Complex is connected to the movement of tectonic plates and the thermal activity beneath them. But how did scientists determine the cause? Well, the rift lies deep underwater in complete darkness. That wasn't a problem for researchers. They sailed to the site on a research vessel and used a powerful sonar system to create a detailed map of the area. After obtaining a clear picture of the terrain, they selectively retrieved volcanic rock samples from different parts of the trench using a chain bag dredge. After that, they delivered the samples to laboratories for chemical analysis. All of this data helped scientists discover that between 37 and 24 million years ago, this part of the North Atlantic temporarily became a boundary zone between the European and African tectonic plates. Tectonic plates are enormous slabs of rock that cover the Earth's crust like a planetary-scale mosaic. They move, collide, overlap, and push away from one another. The King's Trough Complex formed during a period when the Earth's crust was splitting apart because of the movement of tectonic plates. It pulled away from east to west, resembling a giant zipper being undone. Now, in addition, scientists found evidence that the crust in this area was subjected to intense heating, rising from deep within the planet. Although researchers don't know exactly what occurred, it's likely that hot material, known as a mantle plume, rose toward the surface. All of these events deformed and fractured the Earth's crust, leaving us with what could be called an underwater Grand Canyon. But why are we interested in this at all? What does knowledge of events that happened tens of millions of years ago give us? Well, scientists now better understand how processes deep within the mantle can influence the movement of tectonic plates. This major research also provides insight into the geological evolution of the Atlantic seafloor. All of it helps humanity better understand similar processes taking place today. For example, near the Azores, another giant system of trenches known as the Tercera Rift is forming right now. What will happen next to this rift? Is such an event dangerous for people? One of the reasons scientists conduct these studies is to answer questions like these. It's unknown what secrets may still be hidden within that underwater fracture, But let's return to land and our beloved Grand Canyon. Even though it is famous worldwide, there are things inside this canyon that may surprise you. The Grand Canyon is ancient, yet it continues to change. Rock erosion happens slowly, but with each passing year, the canyon grows deeper and its shape evolves. Now, if you plan to visit the Grand Canyon, prepare for unpredictable weather. The canyon has its own climate, which can differ from the surrounding region. Because of the dramatic elevation changes, temperatures constantly shift. Snow may fall along the rim, while not far below, people inside the canyon enjoy warm sunshine. Walk a little farther and higher, and you might find yourself in the rain. Take shelter lower down, and you could end up surrounded by fog. So plan your route carefully and check forecasts from official weather services. There's both good and bad news for archaeologists. In the Grand Canyon, you can find ancient fossils of marine creatures more than 1 billion years old. In its caves, there are traces of land mammals dating back 10,000 years. The bad news is there are no dinosaurs here. The canyon most likely formed after those ancient reptiles became extinct. Now, one thing that may surprise you during a hike through the Grand Canyon is Supai Village, with a population of about 200 people. It's located at the base of the canyon within the Havasupai Indian Reservation. It's the most remote settlement in the continental U.S. and the only place in the country where mail is still delivered by pack mule. There are no roads leading to the village, and if you want to visit it, you'll need to prepare for a challenging hike along steep slopes under the blazing sun. Beyond its fascinating natural features, the Grand Canyon also has things that are almost fantastical and eerie, at least according to rumors and legends. For example, there's a hotel room known as the Grand Canyon Cavern Suite inside the canyon, deep within one of the caves. At a depth of 220 feet, guests find a luxurious room with all the comforts and, according to some accounts, something unsettling. Some visitors have reported stones moving inside the room, frightening dancing shadows, strange sounds, and movements near the bed where they were sleeping. You might also hear many local legends about spirits and monsters that inhabit the canyon. Of course, these are just stories, but some truly tragic events have taken place here. The canyon has become a grave for many people. Over time, around 800 people, according to official records, have passed away here. There were accidents, mysterious incidents, and real tragedies. For example, in 1956, 2 airplanes collided in the sky above the canyon. And that was far from the only case. So be careful when you come here. Stay away from the cliffs and keep close to your group. There is also a theory that ancient advanced civilizations once lived in the Grand Canyon. These rumors began in 1909 when a local newspaper published a major article claiming that 2 archaeologists from the Smithsonian Institution had discovered a secret tunnel filled with Egyptian artifacts and mummies. The Grand Canyon and ancient Egypt? How could that be possible, considering the vast distance between them? Soon after the article was published, the Smithsonian Institution issued a denial. No archaeologist from the institution had conducted such research, and certainly none had found Egyptian artifacts. Many believe the newspaper had published a hoax, although some suggest the institution deliberately concealed information about hidden discoveries. In any case, the story seems highly unlikely. Now, even though you know all this and want to see something similar yet different, you should travel to Tibet, where the Yarlung Zangpo Canyon is located. It is 2 miles deeper and 30 miles longer than the Grand Canyon. There, you would also see many fascinating things, but that's a topic far too large and deserves another video.
We are on the Sea of Marmara, the exact spot where the massive continents of Europe and Asia meet. It's a vital, beautiful waterway packed with cargo ships on the surface, but dive underneath and you'll find a geographical nightmare lying on the seafloor. Deep underwater, two massive slabs of the Earth's crust are violently grinding past each other. This isn't just a minor crack in the dirt, it's a colossal geological fault. A massive complex system of continuous fractures that has been accumulating a devastating amount of energy for decades. We call it the Great North Anatolian Fault. All this energy has to be unleashed someday. And when it happens, it's going to hit one of the most densely populated areas on our planet. Scientists are now in active monitoring mode, especially when it comes to Turkey. This country is sitting on the Anatolian plate, a small bite of the Earth's crust. Nowadays, it's being literally smashed by the Arabian plate from the south and the Eurasian plate from the north. Because it's being squeezed so hard, the only direction it can move is west toward the Aegean Sea, and it actually does this at a speed of about 1 inch per year. In geological terms, that's a high-speed, violent movement. Millions of tons of solid rock grinding against each other deep underground day and night without a single break? Not the best thing to experience. All this endless moving, cracking, and squeezing is what creates the North Anatolian Fault, a 930-mile-long fault line that acts almost exactly like the infamous San Andreas Fault. Yet the difference is striking. While the San Andreas mostly skirts the outer edges of Californian megacities or runs through less dense regions, the fault in Turkey is running right under major industrial hubs and heavily populated urban centers. In February 2023, the smaller sister of it, the East Anatolian Fault, showed us how dangerous this tectonic setup can be. It generated the most catastrophic earthquake recorded in Turkey in over 60 years, a brutal 7.8 monster hit and a 7.5 shockwave followed right behind it just hours later. The release of energy was so violent that the ground literally moved by almost 10 feet in some places. Entire cities were leveled and the physical map of the region permanently shifted. Now the worst part, it wasn't even the grand finale. There's no way to stop that energy packed inside the North Anatolian Faults. Look at the old data and you'll see it acts like clockwork, a bit like a line of falling dominoes. Scientists have been tracking every sequence of earthquakes in this region for nearly a century. The whole chain reaction started in 1939 with the catastrophic Erzincan earthquake. A massive magnitude 7.8 struck eastern Turkey. It didn't simply release the energy, but also transferred this tectonic stress into the next section of the fault. Dominoes started falling. Other fault rupture happened in 1942, 1943, and 1944. It went west and struck again in 1957 and 1967. Year by year, the epicenters of these massive earthquakes moved in a straight line toward the Sea of Marmara. The last major impact was the Izmit earthquake in 1999. A magnitude 7.6 tremor struck east of Istanbul and lasted for 37 terrifying seconds. Suddenly, the chain reaction took a break, but the tectonic stress was still there, simply transferred to the next section of the fault, under the Sea of Marmara, where the last major earthquake took place in 1766. Nobody had seismographs back then, but historical records and old journals describe it as a scene of unimaginable horror. Now, modern science tells us exactly why it was so devastating. Scientists are calling it a seismic gap, basically a dangerously quiet zone that hasn't ruptured yet. Back then, 260 years ago, a massive quake destroyed a huge part of Istanbul and generated a tsunami that crashed into the city's ports. After this tragedy, it didn't happen again on this scale, but we have to remember that the Anatolian plate has never stopped moving west, an inch a year. Let's do some quick math. That land should have moved by over 19 feet by now, but because those rocks are locked together, they haven't moved an inch. We are looking at a massive backlog of tectonic tension. It simply has to snap finally, and it won't make a regular shake. it will likely rapidly release 2.5 centuries of accumulated tectonic energy, right at the doorstep of Europe and Asia. The target is the city of Istanbul once again. We should call it a supercity because this global mega-hub is home to an astonishing 15 million people. It accounts for nearly 30% of Turkey's entire economic output. What about the infrastructure? We're talking about 1 million buildings, and an estimated 90,000 of those are at high risk of total collapse in the event of a magnitude 7.5 earthquake. Nowadays, the city has very strict laws for modern buildings. But plenty of urban areas had been built before those regulations were enforced. To make matters worse, many coastal neighborhoods are built on soft, waterlogged soil that acts like a liquid during extreme shaking, multiplying the danger for the residents. Buildings could just sink into quicksand. And there's more. The seafloor of the Marmara Sea isn't flat. There are 3 massive deep underwater holes separated by vast ridges. Why is it important? A stronger earthquake in this area will probably trigger a massive submarine landslide. Plenty of mud and rock collapsing down those underwater canyons would instantly displace massive amounts of water. This would trigger a tsunami, not as tall as mega tsunamis in the open Pacific Ocean, but still highly dangerous. It's estimated that with a 10-foot wall of water, it will be extremely dangerous for this densely populated area. Scientists also claim that it could hit the coastline within 10 minutes. There would be almost no time for a mass evacuation. Here comes modern technology. Engineers are fully aware that this geographical clock is ticking and are fighting back. Essentially, infrastructure is being heavily retrofitted. Also, the mighty bridges crossing the Bosphorus Strait have been reinforced with seismic dampers to absorb extreme shocks. One of the world's largest seismically isolated buildings is located at Sabiha Gökçen International Airport in Istanbul. It's sitting on massive bearings made out of rubber and steel. The absolute art of engineering is the Marmara Tunnel, a massive railway tube that runs directly under the Bosphorus Strait, physically connecting the European and Asian continents underwater. It was built right next to an active fault line, so it had to be designed with flexible earthquake-proof joints. If a megaquake hits and the continents shift, the tunnel will bend and flex like a giant snake rather than snapping in half. Another concern of scientists is the economic aftershock of this rupture. It may affect the entire globe, as the Bosphorus Strait is one of the world's most critical maritime choke points. Every single year, nearly 50,000 ships pass through this narrow waterway, carrying everything that is crucial for the global market: barrels of oil, agricultural goods, and so on. The price of energy and food would go crazy if this shipping line collapses. To buy some precious time, scientists have installed an advanced early warning network on the seafloor of the Marmara Sea. Fiber optic cables and seismometers are constantly listening to the fault. But because the epicenter is located so incredibly close to the city, even this multi-million-dollar system won't give residents enough time to escape. At best, it will provide a maximum of 5 to 7 seconds of warning before the destructive waves hit the city. 5 seconds to shut down gas lines, halt the trains, and brace for the impact. Of course, all this effort won't protect the whole city. Only a fraction will survive. The undeniable conclusion is that the migration of earthquakes isn't just a theory, but a well-documented geographical reality. Scientists estimate that there is a 65% probability of a magnitude 7 or greater earthquake striking the Sea of Marmara region before the year 2030. Now we can see that the rupture in this area isn't just a possibility. It is coming, and it is migrating directly toward the collision point of 2 continents. Australia feels like the safest place on Earth, geologically speaking. No megavolcanoes, no massive fault lines slicing cities in half, no constant earthquake alerts. It looks solid and unbreakable, but according to a brand new global stress map of Earth's crust, Australia is one of the most internally stressed pieces of land on the entire planet. It's not shaking or cracking yet, but it's quietly storing energy like a bent ruler about to snap. To understand why this is such a big deal, imagine Earth's crust like a giant jigsaw puzzle made of moving slabs called tectonic plates. These plates float on softer rock below and push, pull, or grind against each other. Where plates meet, earthquakes and volcanoes make sense. But stress doesn't just stay at the edges, it travels. It builds up inside plates too, like pressure spreading through frozen ice when you squeeze it. Scientists mapped over 100,000 real stress measurements from oil wells, rock tests, and earthquakes to see where Earth is being squeezed the hardest right now. When they laid all the data together, the map lit up like a warning sign, and Australia stood out. This shocked scientists because Australia sits far away from plate boundaries, which usually means stability. But instead of relaxing, the Australian continent gets squeezed from multiple directions by nearby plates, especially the Pacific and Eurasian ones. The stress doesn't release easily, so it piles up inside the crust, and then nothing moves. Until suddenly everything does. One of the strangest discoveries showed up in places like the Bowen Basin, where stress directions twist and rotate underground. That's bad news because unpredictable stress behaves like glass about to shatter. These rotating stress fields make it nearly impossible to say when or where cracks could form. It could be years away or tomorrow. And human activity makes it even riskier. Drilling deep into the crust for geothermal energy or injecting fluids underground can nudge these stressed zones just enough to trigger fault movement. This doesn't mean Australia is about to split in half next week, but it does mean the idea of geologically safe might be outdated. Scientists now think Australia could eventually fracture internally and form new fault systems where none existed before. What makes the new stress map different from older models is that it doesn't just explain past earthquakes, it helps identify future risk zones before anything breaks. Countries can use this data to decide where drilling is safer, where tunnels shouldn't go, and where infrastructure needs reinforcement. But even with all this data, we still can't predict the exact moment Earth will snap. Stress maps tell us where the tension is. They don't tell us when it gives up. But this idea of continents quietly tearing themselves apart isn't just theory. Africa gives us the clearest real-world example. It's slowly unzipping itself. So slowly that no human will ever wake up and see a new ocean where land used to be, but fast enough that scientists can actually measure it happening right now. Deep beneath East Africa, the ground stretches, thins, and pulls apart as if the continent is taking a deep breath and never fully exhaling. And over millions of years, that stretch could turn into an ocean. This whole process centers on something called the East African Rift System, or EARS for short. Think of it like a giant tear running through the continent, thousands of miles long, cutting through countries like Ethiopia, Kenya, Tanzania, and Mozambique. It's one of the biggest rift zones on Earth. A rift zone is exactly what it sounds like, a place where the planet's crust is being pulled apart instead of squeezed together. And Africa just happens to have one of the most dramatic examples anywhere on the planet. What's really happening is that Africa isn't one solid plate anymore. It's splitting into two massive chunks, the Nubian plate to the west and the Somalian plate to the east. These two plates are drifting away from each other at a speed that sounds laughable, just less than an inch per year. That's about the speed your fingernails grow. But give that process millions of years and suddenly continents don't look so permanent anymore. In 2018, photos of a giant split in Kenya went viral across the internet. Headlines screamed that Africa was splitting in half right now. It looked dramatic, but that moment didn't mean Africa suddenly broke overnight. That rupture was more like a surface ripple, a small local sign of a much bigger process that's been going on for around 25 million years. And if we could travel in time to 5 or 10 million years from now, we would probably see the crust thin enough for seawater to rush in. When or if that happens, East Africa would slowly peel away from the rest of the continent, and a brand new ocean basin would form between the two plates. Africa would lose its eastern shoulder, and maps of the world would need a serious update. As strange as that sounds, it's actually totally normal for Earth. The planet never stops reshaping itself. It just works on a timeline so slow that our brains struggle to process it. The continents we know today feel ancient and permanent, but they're basically temporary arrangements. About 138 million years ago, South America and Africa were locked together like puzzle pieces. You can still see it if you look at their coastlines. They match almost perfectly. East Africa drifting away will just be the next chapter in that story. Australia's story could follow a different path, but the physics are similar. Stress builds, rock resists, then the rock fails. And stress doesn't care about borders, cities, or how calm the surface looks. That's why scientists are so concerned about something called SH max, the direction of maximum horizontal stress. In simple terms, it tells us which way the Earth is squeezing the hardest underground. If that squeezing lines up with existing fractures, earthquakes become more likely. If it cuts across old faults, new ones can form. Turkey is another place where the stress map practically screams danger. The country sits where Arabian, Eurasian, and African tectonic plates collide. There's also a smaller Anatolian plate on which Turkey is located, and which gets squeezed westward like toothpaste, grinding against massive faults. The stress map shows SH max pointing in directions that load these faults perfectly. Now, researchers looked at ancient lava flows near one of Turkey's faults and realized they weren't random. Lava sheets once flowed smoothly across the land, cooled into solid rock, and then got pulled apart over time, like a snapped chocolate bar. That gave scientists a rare, clear snapshot of how continents deform from the inside out. To date the lava, the team used microscopic zircon crystals trapped inside it. These crystals work like natural stopwatches. They trap helium created by radioactive decay, and by measuring that helium, scientists can tell when the lava erupted and cooled. When they combine that with satellite images and remote sensing, the scientists managed to see Earth's slow-motion movements. The Tuzgolu Fault stretches more than 120 miles and is so massive that you can spot it from space. For years, scientists assumed it behaved like many of Turkey's dangerous faults, where land slides sideways past itself. But this new research flipped that idea on its head. The fault isn't sliding, it's slowly ripping open. The land on either side moves away from each other at less than an inch per year. That sounds tiny, but then again, over thousands or millions of years, that motion adds up to continents literally thinning and breaking. And since the fault sits where three massive tectonic plates meet, this matters way beyond Turkey. All this once again reminds us that continents don't just collide or slide. Sometimes they stretch until they snap. And places that look calm on the surface might already be under invisible strain, inch by inch, year after year, rewriting the map long before anyone feels the shake. Right now, as you read this, two colossal slabs of rock are locked against each other beneath the streets of Oakland, California. It sounds like nothing to an unprepared person, but the problem is that they're pressing harder with every passing year, storing up energy like a spring that's been coiling for more than 150 years. Roughly 30 feet below the sidewalks where people walk their dogs and grab their morning coffee, a geological clock has already run out. And scientists now know with uncomfortable precision exactly what happens when it finally lets go. This is the story of the Hayward Fault, one of the most dangerous strips of land in the United States. And the extraordinary computer simulations that are finally revealing the full picture of what the next big earthquake will do to millions of people. Let's start with the fault itself, because the Hayward Fault is not some distant geological curiosity hiding far out in the wilderness. It runs for roughly 74 miles right through the heart of California's East Bay, directly under neighborhoods, schools, hospitals, and highways, in cities like Oakland and Berkeley. More than 2 million people live or work along its path. And it is, by scientific consensus, overdue. The last time the Hayward Fault produced a major rupture was in 1868. That earthquake, estimated at magnitude 7, was devastating by the standards of the time. It flattened buildings across Hayward and sent shockwaves all the way into San Francisco. But here is what makes today's situation so much more serious. The fault's average cycle between major earthquakes is around 140 years. We are now more than 150 years past that last rupture. The clock has not just run out, it ran out over a decade ago. The numbers from the United States Geological Survey make this concrete. There is roughly a 1 in 3 chance of a magnitude 6.7 or larger earthquake on this fault within the next 30 years. But the Hayward Fault doesn't operate in isolation. When scientists factor in connected faults in the region, including the nearby Rogers Creek Fault to the north, the probability of a major rupture somewhere in the system climbs to 72% by the year 2043. That is not a distant hypothetical. That is a near certainty within most people's lifetimes. So what exactly happens when it breaks? For decades, the honest answer was, we're not entirely sure. General earthquake models existed, but the Bay Area's geology is complex, a patchwork of hard rock, soft sediment, deep basins, and hill formations. And predicting how seismic waves travel through that maze was beyond the computing power available. That changed recently. Researchers at Lawrence Livermore National Laboratory and Lawrence Berkeley National Laboratory used some of the most powerful supercomputers on Earth to run 50 separate simulations of a magnitude 7 earthquake on the Hayward Fault. Each simulation varied the details, where exactly the rupture starts, how the slip spreads across the fault surface, how fast the break travels. The result is not one prediction, but a rich, detailed map of possibilities, showing not just where shaking will occur, but how intense it will be, how long it will last, and why certain neighborhoods face dramatically higher risks than others. What they found should reshape how every Bay Area resident thinks about where they live. The most important takeaway from these simulations is this: the ground does not shake equally. Location matters enormously, and the differences are not subtle. Take the Eastern Hills, places like Orinda and Moraga. These communities sit on layers of softer sedimentary rock, and that geology acts like an amplifier. In a major Hayward Fault earthquake, shaking in these areas could be up to 50% more intense than in western neighborhoods sitting on solid bedrock. That is not a rounding error. That's the difference between a building that survives and one that doesn't. And then there's Livermore Valley, which faces a different but equally serious problem. The valley sits in a geological basin, and seismic waves behave strangely inside basins. They bounce around, trapped between the basin walls, unable to escape. Instead of the shaking lasting the usual few seconds, simulations show it could continue for more than 2 minutes in Livermore. 2 full minutes of sustained, violent shaking. For pipelines, warehouses, and industrial infrastructure, that duration is potentially catastrophic. In Oakland and Berkeley, right on top of the fault line itself, the main danger comes for what scientists call directivity pulses. When a pulse ruptures, the break doesn't happen all at once. It races along the fault, and in doing so, it flings concentrated bursts of energy forward like a wave from a moving source. Communities directly in the path of that forward momentum get hit with sharp, powerful pulses that are particularly destructive to tall buildings. Skyscrapers and high-rises in these cities face the highest risk from this effect, with ground accelerations that can reach the equivalent of the full force of gravity. Enough to overwhelm structures that were not built with this specific threat in mind. Meanwhile, on the western side of the Bay Area, underlain by the hard Franciscan bedrock, things look noticeably different. Ground acceleration there could be 20 to 50% lower than in the highest risk zones. San Francisco itself will certainly feel the earthquake, but distance and solid geology provide meaningful protection. This does not mean Western neighborhoods are safe. It means they are safer, relatively speaking. To understand why geology creates such stark differences, it helps to think about how seismic waves actually move. When a fault ruptures, it sends waves radiating outward in all directions, much like dropping a stone into a pond. But unlike water, the ground is not uniform. Hard bedrock transmits those waves quickly and efficiently, so energy passes through without lingering. Soft sediment, by contrast, slows the waves down, compresses them, and forces them to grow taller and more violent. The same way ocean waves rear up and crash when they hit shallow water near the shore. The Bay Area sits on an extraordinary variety of ground materials, which is precisely why two neighborhoods just a few miles apart can experience the same earthquake in dramatically different ways. The simulations capture this complexity in finer detail than any previous model, and the results make clear that geology is not just a background detail, it's the single biggest factor determining who gets hurt and who walks away. What makes these simulations genuinely groundbreaking is that they don't just produce abstract data, they produce actionable intelligence. Engineers can already use these results. For skyscrapers in Oakland and Berkeley, the pulse wave risk means buildings need reinforcement specifically designed to absorb those sharp, sudden jolts rather than the slower, rolling motion of distant earthquakes. In Livermore, foundations for new construction must account for extended shaking durations, not just peak intensity. In the eastern hills, slope stability becomes a critical concern. Steep hillside homes face elevated landslide risk when shaking amplifies. For public infrastructure, Bay Area Rapid Transit, BART, and the region's freeway systems are being prioritized for retrofitting based on the directivity cone maps and simulations produced. The fault doesn't just threaten buildings, it threatens the transportation networks people will desperately need after a major event. And for ordinary residents, the implications are personal and practical. Securing heavy furniture, water heaters, and bookcases reduces injury risk. Early warning apps can provide seconds of notice before shaking arrives, enough time to drop, cover, and hold on. Emergency supplies for at least 3 days are not excessive preparation. For a region this exposed, they are basic common sense. The science of earthquake prediction is moving fast. These simulations are already being extended to the San Andreas Fault, modeling potential magnitude 7.5 or larger events. Higher resolution subsurface mapping will push the models to even finer detail. But the Hayward Fault simulation already tells us something profound. We do not need to be helpless in the face of this threat. The ground beneath the Bay Area is not a mystery anymore. We know where the danger concentrates. We know why some neighborhoods will shake harder, why some valleys will shake longer, and why some buildings face risks that others don't. The question is no longer whether this earthquake is coming. The question is whether we will be ready when it does. A leftover chunk of an ancient tectonic plate is on the move beneath North America, right under the southern part of the Cascadia subduction zone. This isn't some harmless debris. It's a real slab of earth that never fully disappeared. And because it's still sliding around down there, it could be adding a whole new layer of stress to a region that already has a reputation for massive earthquakes. The story started with weird signals showing up in seismic data. It's basically Earth's X-ray. Scientists send waves through the ground and watch how they bounce back. These waves started acting wrong beneath the Pacific Ocean off the western US coast. Instead of smooth, predictable patterns, researchers saw a giant, coherent block deep below the seabed, moving differently from everything around it. It didn't look like a landslide, didn't look like loose debris, and didn't behave like normal ocean crust. That's when someone dared to ask the question out loud. What if this is something much older and much bigger than we thought? Some researchers seriously wondered if this could be a remnant of a lost continent, maybe a forgotten shard of Pangaea. the supercontinent that once stitched almost all land together. Technically, it's not fully impossible. Continents break, sink, stretch, and vanish over millions of years. This fragment was enormous, solid, and oddly shaped, which made it hard to classify. It didn't fit into the usual categories scientists use to explain underwater structures. Then came the slow, careful reality check. Scientists brought in more data, better models, and deeper analysis. They measured the age of the rock, studied how seismic waves bent through it, and compared its motion to known plate movements. That's when the picture shifted. This wasn't a lost continent at all. It was something just as dramatic, but far more dangerous. A massive leftover fragment of an ancient tectonic plate. This fragment turned out to be a survivor from the Farallon Plate. This ancient plate once dominated the Pacific, but got mostly swallowed as it slid beneath North America millions of years ago. Most of it vanished into Earth's mantle, but not all of it went quietly. This chunk survived like a splinter that never fully sank. Researchers named it the Pioneer Fragment, and the name fits because it's charting territory we didn't even know existed. And this fragment isn't just drifting harmlessly, it's moving horizontally beneath North America, which is weird and dangerous in geological terms. Normally, plates collide or slide past each other in predictable ways. This fragment behaves like a wrench jammed into a machine that already runs under insane pressure. The West Coast already balances on fault lines that store stress like stretched rubber bands. Add a giant moving rock slab underneath, and suddenly the system becomes harder to predict, harder to model, and much harder to feel safe about. The region where this fragment lurks already scares geologists. You've got the San Andreas Fault, famous for snapping without warning. You've got the Cascadia subduction zone, capable of producing earthquakes so powerful they rewrite coastlines. Now, scientists realize there's a hidden player deep beneath the ocean floor, something satellites can't see, and scientists can't directly observe. This fragment doesn't follow clean, predictable rules. Think of it like stacking dominoes on a table that's already shaking. It moves slowly, but in geology, slow movements still means unstoppable force. And when that built-up energy is finally released, it won't care about evacuation plans or building codes. There's also a timing problem that nobody likes to talk about. Geological processes don't run on human clocks. Stress can build for centuries and snap in seconds. The Pioneer Fragment might trigger something tomorrow, or it might sit quietly until generations forget about it. That uncertainty makes planning brutally hard. Cities like Los Angeles, San Francisco, and Seattle already prepare for known earthquake threats. Now, scientists must consider a system that can amplify disasters in ways nobody has practiced for. So, scientists now race to update models, improve seismic imaging, and understand how this fragment interacts with nearby faults. They know they can't stop earthquakes. All they can do is reduce surprises. And it's also clear that sometimes the most dangerous threats aren't coming from space, but sliding quietly beneath the sea. Another recent ancient landmass discovery wasn't nearly as dramatic, but super important for science. It started as a sand dredging operation off the coast of Indonesia, but then archaeologists found more than 6,000 fossil fragments from a lost submerged ice age landmass. Among them were 140,000-year-old Homo erectus remains. That single find forced scientists to rethink how early humans lived, moved, and interacted across Southeast Asia. For a long time, researchers assumed the Homo erectus population on Java lived cut off from everyone else. But those dredged-up fossils proved that Java wasn't an island. It sat right in the middle of a massive Ice Age landmass called Sundaland. Indonesia, Malaysia, Borneo, Thailand, and Vietnam are all connected into one enormous landscape. But we now call islands like Java, Sumatra, Borneo, and Bali were linked together through huge river systems that probably rivaled the Amazon. Dense forests stretched across the land, giant animals roamed freely, and wide coastal plains existed where ocean waves sit today. And Homo erectus didn't just survive there, they thrived. And no, this wasn't a snowy wasteland, unlike how we mostly imagine the Ice Age. sea levels dropped more than 400 feet because so much water was locked up in glaciers. When that happened, massive chunks of the ocean floor rose above the surface like natural stepping stones. Early humans didn't need boats. They could literally walk from mainland Southeast Asia to places we now think of as isolated islands. They moved while tracking animals, exploring open land, and following food sources. It worked like a giant prehistoric highway system. When the Ice Age ended, glaciers melted like forgotten ice cream cones on a hot sidewalk. Sea levels rose, slowly at first, then fast. Rivers overflowed, coastlines vanished. Entire human landscapes slipped beneath the waves. Over thousands of years, Sundaland drowned, and the people who lived there had to adapt or move to higher ground. Now, archaeologists piece together this lost world bone by bone, artifact by artifact. Every new discovery pulled from the seabed brings us closer to rewriting the story of early human migration. Studying submerged landmasses and lost continents is a work that takes years. In 2017, scientists made an announcement that changed this universal truth that there are 7 continents in the world. The discovery of Zealandia. Zealandia's story ties straight back to Gondwana, the ancient supercontinent that started breaking apart hundreds of millions of years ago. Around 80 million years ago, Zealandia split off too. But while Australia stayed high and Antarctica mostly held its ground, Zealandia slowly sank. Only a small chunk stayed above sea level, even though many geologists argue it still qualifies as a full continent. That little bit you can actually see today is mostly New Zealand, along with a few nearby islands that also belong to Zealandia. By the end of 2025, scientists had finished mapping the northern 2/3 of it, covering nearly 2 million square miles of submerged land. Researchers dredged rock samples all the way from the Fairway Ridge to the Coral Sea. They pulled up all kinds of material: pebbly and cobbly sandstone, fine-grained sandstone, mudstone, bioclastic limestone, and even basaltic lava. And these rocks came from wildly different time periods. When researchers lined all this up, they saw something big. The internal stretching from both Zealandia and West Antarctica caused the crust to thin and crack in a way similar to subduction. That cracking let ocean water rush in and helped form the Tasman Sea. A few million years later, Antarctica continued pulling away, stretching Zealandia's crust even more until it thinned so much that sinking became inevitable. This directly challenges the older idea that Zealandia broke apart mainly through sideways strike-slip motion. The team also thinks the direction of that stretching shifted by as much as 65 degrees, which likely helped the continental crust thin out way more than expected.
Here you are in a park, enjoying a normal day, when suddenly dark, muddy clouds appear above you. But this doesn't last minutes or hours. It goes on for weeks, and everything around you is slowly starving for sunlight. This is exactly what happens on the ocean floor, and scientists gave it a name. They call it marine dark waves. You may have heard of underwater heat waves. This is when the ocean gets way too hot and stays this way for weeks or months. This happens because the ocean acts like a giant sponge for the planet. When the atmosphere traps heat from the sun, the ocean soaks it up. Sometimes, warm currents get trapped in one spot, like hot water swirling in a bathtub, slowly cooking everything trapped inside. The heat wipes out stuff that can't move, like corals or seagrass, while fish either flee to cooler waters or struggle as oxygen levels drop. Because these plants and reefs sit at the base of the food web, the damage ripples through the entire ocean ecosystem. Marine heat waves are a huge problem. However, dark waves are almost equally bad, but in a completely different way. A marine dark wave is obviously not about the heat. It's about light suddenly disappearing where it's supposed to exist. If we can imagine the ocean like a giant glass building, where sunlight normally pours through windows and lights up every floor, dark waves would be like someone filling that building with thick smoke. It happens when the water gets clogged with a thick, swirling soup of turbid matter. The water itself becomes a light-eating fog. Basically, mud, sand, algae, and all kinds of microscopic organic junk gets stirred up and suspended in the water, scattering and absorbing sunlight before it can reach the seafloor. When it gets thick enough, the seafloor disappears into darkness. This starves any life at the bottom that depends on the sun for food. And the strange thing is, we're not talking about a deep dark ocean miles below, where sunlight never reaches anyway. All of this happens near the coast, right in the shallow parts where underwater plants need the sun to survive. What makes dark waves especially tricky is how easy they are to miss. From the surface, everything can look normal, even to satellites. You can park a boat on top of a dark wave and still not notice anything weird. That's why this phenomenon went largely unnoticed and wasn't properly studied until recently. To properly catch whatever was turning off lights at the seafloor, scientists started cross-referencing data like detectives. They had to dig through archives and build a kind of time machine out of old data. They gathered 16 years of continuous light readings taken directly from the bottom of the Santa Barbara Channel. Then they matched that with more than 20 years of satellite-based light data from the coast of New Zealand. They essentially rewound the security camera footage of the ocean for the last 2 decades to see what they had missed. With all that data combined, researchers found a specific event in New Zealand where the seafloor received almost no usable sunlight for 64 days. Imagine if the sun set on the 1st of November and didn't rise again until after New Year's Day. If that happened on land, it would be a disaster for anything that needs sunlight to grow. Think about your houseplants. If you shoved a fern in a closet for a week, it would probably look a bit sad, but it'd bounce back. But if you left it in there for 2 months, it'd turn yellow and slowly wither away. On a larger scale, if a forest lost the sun for 64 days, the undergrowth would rot. That would cause deer and other animals to run out of food, and the whole food chain would get shaky. It's a similar biology for the underwater world, because it also needs the sun. Down there, instead of pine trees and grass, you have giant kelp forests and seagrass meadows. They're like the oxygen gas stations of the sea. They take sunlight and turn it into fuel for the entire ecosystem. When a long dark wave hits, it drains their batteries until nothing grows back. The same thing happens to kelp. It starts to deteriorate. The fish that munch on it go hungry, and suddenly, a vibrant underwater city turns into an underwater ghost town. Marine dark waves don't just affect underwater plants. They can even affect those higher up on the food chains. We often assume that sea animals hunt by scent, but they actually depend heavily on sunlight. Many sharks and large fish rely on sunlight in contrast to hunt. They're built to spot dark shapes moving against brighter water, especially when sunlight filters down through clear water. Think of it like watching shadows move behind a white curtain. Even in low light, that contrast pops. But a marine dark wave wipes that away. The water turns cloudy, the background goes dark, and the silhouettes simply disappear. Sharks still have other senses, like picking up tiny electrical signals from nearby animals, but that only works when they're close. They're not blind, but it feels like trying to hunt in a room filled with thick smoke. You can still feel things close by, but anything further away is invisible. Apex predators don't pass away easily, but their hunting efficiency drops, which changes who eats, who escapes, and who goes hungry. That confusion stretches all the way to the docks. Fishing towns depend on marine life behaving predictably. If fish can't feed, they move on. That leaves nets empty and boats coming back light. Boat captains can read a weather radar to dodge a storm, but there is no forecast for the ocean running out of light. It also creates a headache for professionals working below the surface. Sonar helps, but divers and research teams still use their eyes. A dark wave alters how light travels through the water, turning a familiar worksite into a murky haze. Navigation becomes a guess. Surveys fail. It is a new stress factor, one the experts never planned for because, until recently, it wasn't even recognized. We've talked about how dark waves happen, but what triggers them? Well, most of the time, it's something loud and chaotic on the surface. Events like major storms and floods, rivers exploding with runoff. When huge storms hit land, they tear soil, mud, and organic matter off the landscape and flush it straight out into the ocean. All that material spreads out into massive underwater plumes that can turn clear coastal water into chocolate milk almost overnight. Scientists can spot surface sediment plumes clearly, but they can't always tell you how dark it gets down on the seafloor. Coastlines darken as sediment clouds expand. The sun might be shining above, but the water is so full of particles that no light can get through. Coastal currents often trap this murky water in place, so the darkness lingers long after the rain stops. That's why dark waves often show up after extreme weather. This creates a deceptive gap. The storm passes, and we assume the recovery has started. But underwater, the water column is still loaded with light-blocking debris. What looks like a return to normal on the surface is actually weeks of extended gloom below. As storms get stronger, we see more of these dark wave situations showing up. The ocean is getting slammed with intense mud and organic plume events that are causing this. Heavy rain leads to more floods and landslides, turning rivers into speedy conveyor belts that dump tons of soil and debris into the sea. Even after the storm passes, waves and currents can keep that cloudy mess swirling around, making the water stay murky for a while, like a shaken snow globe. So, what's next? Scientists are finally taking marine dark waves seriously instead of brushing them off as some spooky ocean myth. Now that we've got a name for these lights-out events and a way to track them, the next step is simple. We need to set up more light sensors in key spots. We also need to figure out how dark waves relate to storms, runoff, and algae blooms. Finally, we need to pinpoint the moment when ecosystems can't bounce back anymore. Basically, we're creating an underwater sunlight weather report because it turns out the ocean just doesn't have storms and heat waves. Sometimes it has its own kind of eclipse.
Most people think of continents as permanent. Europe is Europe. North America is North America. Their borders feel ancient, pretty much fixed and untouchable. But there is one country on Earth where that illusion breaks apart in real time. Now, I've got a question for you. Which country sits on two continents? If you're a geography guru, you may name countries like Kazakhstan, which is mostly in Asia but does have a small part in Europe. Or maybe Egypt, which stretches from Africa into Asia across the Sinai Peninsula, famously using the Suez Canal as a continental boundary. But I'm talking about Iceland here. You have every right to say, wait, Iceland is in Europe, period. And culturally and politically, you'd be absolutely right. But geologically, that's a completely different story. You see, Iceland is a country where the planet is physically pulling itself open. You can stand with one foot in North America and the other in Europe. Not symbolically. The ground beneath you literally belongs to two entirely different tectonic plates drifting away from each other every single year. And the separation is still happening right now. Every year, the gap grows by roughly 1 inch. That may sound tiny, almost meaningless, but that same slow movement has already reshaped the surface of the Earth. Over tens of millions of years, it opened the entire Atlantic Ocean. It separated land masses that once sat side by side on a single supercontinent. The same force stretching Iceland today is the reason New York and London now sit thousands of miles apart. So no, Iceland is not simply a country with volcanoes. It is one of the only places on Earth where you can literally watch continental drift happening with your own eyes. And it sounds simple when you first hear it. A country between two continents. Cool geography fact. But once you really understand what's happening there, Iceland becomes one of the strangest places on the planet. Because beneath the Atlantic Ocean lies something enormous. The Mid-Atlantic Ridge. This thing is massive, but over 90% of it is hidden underwater, which is why most people have never heard of it. And Iceland is one of the very few places where part of that underwater mountain range rises above sea level. That alone makes the country geologically extraordinary. The Mid-Atlantic Ridge marks the boundary between two gigantic tectonic plates, the North American Plate and the Eurasian Plate. And these plates are not stationary slabs of rock. They move constantly, driven by slow currents of superheated material deep inside Earth's mantle. At Iceland, those plates are diverging, pulling apart, separating inch by inch, just like a bag of chips that you tear open. Normally, this process happens invisibly beneath the Atlantic Ocean. Nobody actually sees continents moving apart because it usually happens under miles of water. But Iceland is different. Iceland sits directly on top of the mid-Atlantic ridge itself, which means you can literally walk across one of the most important geological boundaries on the planet. And probably the best place to see this is Thingvellir National Park in southwestern Iceland. At first glance, the place almost looks unreal. The landscape is ripped apart by enormous cracks and canyons, with jagged black lava fields stretching in every direction. Massive rock walls rise straight out of the earth like the remains of some collapsed ancient world. But these are not just old geological scars frozen in time. These fractures are active. They exist because North America and Europe are still pulling away from each other beneath your feet right now. And most visitors walking through the area have absolutely no idea they are literally standing between continents. In some places, the water filling these fissures is so unbelievably clear that you can see deep into the submerged fault lines below. And the landscape itself is still changing. Over the last 10,000 years, the Thingvellir Rift Valley widened by roughly 230 feet and sank around 130 feet as the tectonic plates kept separating. So this is not some ancient event that happened millions of years ago and then stopped. The process is still happening today, which naturally raises a pretty obvious question. If Iceland sits directly between two tectonic plates moving away from each other, why hasn't the island already split in half? And the answer is what makes Iceland even stranger. As the plates slowly pull apart, pressure deep underground drops, allowing molten rock from Earth's mantle to rise upward and fill the gap. Once that magma reaches the surface, it cools into completely new crust. So Iceland is basically being torn apart and rebuilt at the exact same time. That balance is what keeps the island together. This entire process is known as seafloor spreading, and it is one of the main forces shaping the surface of our planet. As tectonic plates drift apart, magma rises from deep inside the Earth, cools into volcanic rock, and creates entirely new crust. Without this process, the Atlantic Ocean itself would not even exist. Around 60 million years ago, the Atlantic was dramatically smaller than it is today. North America and Europe sat much closer together as leftovers of the ancient supercontinent Pangaea. Then the mid-Atlantic ridge slowly began forcing them apart. It didn't happen through giant apocalyptic explosions or one massive catastrophic event. It happened thanks to simple, relentless movement measured in inches per year. And honestly, that's the part human brains struggle to understand. An inch per year sounds harmless because human lives are short, but geological forces do not care about human timescales. They never stop, and over millions of years, tiny movements become oceans. The Atlantic Ocean itself is basically proof of that, and Iceland sits directly on the fault line where that expansion is still happening today. The island's volcanic activity is part of the exact same process. Iceland is one of the most volcanically active places on Earth, with more than 15 volcanoes erupting there during the last century alone. And this is not random bad luck. Iceland occupies an incredibly unusual geological position because it sits not only on the mid-Atlantic ridge, but also directly above something called a mantle plume. Basically, a massive column of superheated rock rising from deep inside the planet. You can think of it like a giant underground blowtorch constantly feeding magma into Iceland's crust and fueling volcanoes across the island. And the result is a landscape that feels unfinished in the best possible way. Lava fields still warm from recent eruptions, steam vents hissing straight out of the ground, geysers blasting boiling water into freezing air. So while in many countries, geological history feels ancient and distant, and in Iceland, geology feels pretty much alive. Some eruptions there are so large they actually create entirely new land. Fresh lava cools into black volcanic rock, slowly expanding Iceland outward. So even though the tectonic plates are trying to pull the island apart, volcanic activity keeps adding new material back in. Iceland is basically patching itself faster than it can fully split open. Now, that does not mean Iceland is stable in the normal sense. Earthquakes are still common. Cracks can still open unexpectedly. Entire regions rise and sink as magma moves beneath the surface. Scientists constantly monitor the island using GPS stations, satellites, and seismic instruments, because Iceland functions almost like a live laboratory for plate tectonics. And honestly, there are very few places on Earth where researchers can observe continental drift this directly, and even fewer where ordinary people can physically experience it themselves. There's even a location on Iceland's Reykjanes Peninsula called the Bridge Between Continents. It's a small footbridge spanning a fissure created by the separating tectonic plates, and tourists casually walk across it in seconds, crossing from the North American plate to the Eurasian plate. Not gonna lie, that sounds almost fake when you first hear it. Like, a literal bridge between continents? Seriously? But the deeper reality behind it is even stranger. But it all makes sense once you realize continents are not permanent objects. They're fragments of crust floating atop a dynamic planet. They merge, split apart, collide, sink, and reform over unimaginable spans of time. Monaco seems powerful. Wealthy people and Instagram influencers walking outside the casino, posh cars pulling up to elite residences, and a tiny cup of coffee that costs more than a kilogram of freshly roasted beans you could enjoy at Café de Paris. Over 700 under Grimaldis, the same family. This place seems invincible, but this luxury veneer is more fragile than you think. This seemingly unsinkable power could be destroyed within minutes by something far more powerful than money: nature. Well, it's not actually only about Monaco. The French Riviera is pretty long, and the danger hangs over not just France, but Italy too. Especially the Liguria region in the northwest. I know you may be watching this video from somewhere far away, and these places may not ring a bell to you, but you've definitely seen them before, at least as a screensaver once in your life. Well, this beauty could one day be buried under an extremely powerful tsunami. And if the word tsunami gives you Japanese vibes, we can make it à la française and call it radomare or maremoto in Italian. It's true that when most people hear the word tsunami, they imagine giant waves crashing into the coast of Japan, Indonesia, and other countries bordering the Pacific. For decades, the Mediterranean Sea seemed different, smaller, calmer, and far removed from the world's most famous tsunami disasters. But scientists and international organizations are now warning that this perception is misleading. A tsunami in the Mediterranean is not a distant possibility. According to experts, it's something that will almost certainly happen again within the next few decades. Yes, again. The French Riviera has already experienced more than 20 documented tsunamis. The most recent one taking place in October 1979. And strangely enough, it was not caused by nature alone. It was more like an unlucky chain of events. At the time, Nice Airport was undergoing a massive expansion project. Authorities wanted to extend the runway farther into the sea and build a new harbor area. Was it really necessary? Honestly, probably yes. If you look at the map, you'll realize Nice is basically the only major airport serving this whole part of the Riviera. Cannes does have an airport, sure, but it mainly serves private jets. Monaco only accepts helicopters, so technically it doesn't even have an airport. The two closest large commercial airports are in Marseille, about 200 kilometers away, and Genoa in Italy, around 190 kilometers away. Turin is technically another option, but driving there means crossing difficult alpine roads. And the train takes more than 4 hours. So yes, Nice desperately needed that expansion. But during the construction works, a massive underwater landslide was suddenly triggered beneath the sea. Huge amounts of mud and rock collapsed downward like an avalanche underwater. This movement displaced enormous amounts of water and created tsunami waves that struck around 60 miles of coastline. In Antibes, the waves reached more than 11 feet high. The disaster took up to 23 human lives and caused flooding, as well as major property damage. And that's the scary part about tsunamis in this region. They do not always need giant Hollywood-style earthquakes. Sometimes, a collapse beneath the sea is enough. The Mediterranean is smaller and more enclosed than the Pacific Ocean, which means waves can travel toward the coast very quickly. In some places, people may only have minutes to react. So, could something like this happen again? Did the locals learn their lesson? Well, construction along the Riviera never really stops. Nice is currently going through major urban transformation projects as part of a push toward modernization and sustainability. While the historic center and the Promenade des Anglais remain mostly untouched, there are still significant construction zones around the port, Nice West, and the airport area. Nobody is saying current construction will directly trigger a tsunami, but UNESCO is still issuing serious warnings. Their monitoring programs and scientific assessments indicate that there is effectively a 100% chance that the Mediterranean will experience at least 3 tsunamis over 1 meter high within roughly the next 30 years. And 3 feet may not sound very large at first, but tsunami waves behave very differently from normal beach waves. They carry enormous amounts of fast-moving water and energy. Even relatively small tsunamis can flood streets, damage buildings, overturn vehicles, and place thousands of people in danger. This very part of the Mediterranean is unique. It has everything packed together: sea, mountains, and dense coastal cities. In some places, like Menton, the geography is truly one of a kind. Menton is shielded from cold northern winds by the Alps and the Prealps. This traps warm Mediterranean air, giving the town more than 300 days of sunshine every year, and some of the warmest winters on the Côte d'Azur. The city itself is tiny. You could literally walk across it in under 2 hours, and the buildings are pushed very close to the coastline. At the same time, the population density is pretty high, and huge numbers of tourists arrive every year for the Lemon Festival and all things lemon-related. Now, imagine a place this tiny hit by a tsunami. Horrible, right? The tsunami danger specifically in Menton comes from 3 main things: nearby earthquake faults, steep underwater terrain, and crowded beaches during summer. And the key issue is that the danger is not far away. It's literally sitting right offshore. Beneath the sea near Menton lies a giant crack in the earth called the North Ligurian Fault System. It sits only about 12 to 18 miles offshore. Deep underground, 2 giant pieces of the Earth, the African plate and the European plate, are constantly pushing against each other. Most of the time, the movement is slow and invisible, but sometimes pressure builds up until the ground suddenly jerks upward. When this happens beneath the sea, the water above gets pushed upward too, almost like someone slamming a hand into a bathtub. That sudden movement can create a tsunami within minutes. This already happened in 1887 during a large earthquake in the Ligurian Sea. The earthquake affected cities across Italy and France, including Genoa, Savona, Nice, Menton, and even Caen. People reported something terrifying. First, the sea suddenly pulled backward, exposing parts of the beach that are normally underwater. Then the water rushed back toward the coast as a wave. Earthquakes near Menton also triggered underwater landslides. Huge amounts of sand and mud can suddenly collapse downhill beneath the sea, like giant avalanches underwater. When all that material moves at once, it pushes water aside and can generate dangerous waves. Even earthquakes happening far away in North Africa can sometimes send tsunami waves across the Mediterranean toward the French coast. What makes this even more dangerous is how calm the sea usually looks. Menton's sea has very small tides, so the water often appears peaceful and harmless. Because of this, many visitors never imagined that a tsunami could happen there. And during summer, the beaches become packed with families and tourists. If a large wave arrived suddenly, evacuation would become extremely difficult. Now, let's rewind for a second to the Ligurian Sea, because the name may have sounded a little strange earlier. Yes, it does exist. Technically, it's part of the Mediterranean Sea, but many people refer to it separately because of its geography. It sits between northwestern Italy, the French Riviera, and islands like Corsica and Elba. And this entire area is particularly vulnerable. The African and European tectonic plates are colliding right beneath this region. That collision created the beautiful mountains everyone admires today. But it also causes earthquakes, which means many famous cities in this region sit directly inside an active geological zone. Genoa, Pisa, Florence, Nice, Antibes, Menton, and of course, glamorous Monaco, right on the coast. The same force that created the Riviera's beauty is also what makes it dangerous. And because so many towns here are squeezed tightly between mountains and the sea, there's very little room to escape if a tsunami suddenly arrives. That is exactly why scientists and emergency agencies are becoming increasingly worried about this coastline.
Around 250 million years ago, no, I wasn't around then, every continent on Earth was fused together into one gigantic landmass, Pangaea. Then the planet began to tear itself apart. Massive tectonic plates slowly drifted away from each other. Oceans opened, and entire continents were reshaped. Scientists once believed these changes belonged to Earth's distant past. But now, researchers think they are watching the same process happen again, in real time beneath Africa. Deep below eastern and central Africa, the ground is slowly stretching and cracking apart. Scientists have known for years that the East African Rift System could eventually split the continent. But new discoveries suggest the breakup may already be much further along than anyone expected. One of the most important clues comes from eastern Africa, across regions including Kenya and Ethiopia. There, researchers studied a massive fracture zone called the Turkana Rift. This area sits inside the larger East African Rift System, a gigantic scar running roughly 4,000 miles from Jordan all the way down to Mozambique. The tectonic plates here are separating extremely slowly, only about 1/5 of an inch every year. That may sound insignificant, but over millions of years, it adds up to continental-scale destruction. To understand what's happening underground, scientists use seismic imaging, studying how sound waves bounce through deep layers of rock beneath the surface. What they found was startling. At the center of the rift, Earth's crust has become dramatically thinner than surrounding areas. In some places, it's only about 8 miles thick, compared to more than 22 miles further away. Researchers say this thinning process is known as necking. Imagine stretching a piece of Play-Doh. The middle becomes thinner and weaker until it eventually pulls apart. Scientists believe the same thing is now happening to the African continent. Even more intriguing, researchers studying underground gases beneath Zambia discovered rare helium signatures rising from as deep as 100 miles underground. These gases may be coming directly from Earth's mantle. Some scientists think this could be evidence that a completely new tectonic boundary is beginning to form beneath Central Africa. If that's true, the continent may already be entering the early stages of a permanent split. And this would not just create a crack in the ground. In a few million years, magma could begin rising between the separating plates, forming brand new seafloor. Eventually, water from the Indian Ocean may rush into the gap, creating an entirely new ocean that divides part of Africa into separate landmasses. The same tectonic forces once shattered Pangaea and shaped the modern world map. Researchers now believe they may be witnessing the beginning of that process all over again.
Africa is ripping itself apart. A giant crack is tearing through the continent and stretching south like a zipper being pulled open. And it's happening faster than anyone expected. Now, scientists think the main trigger might not be buried deep inside Earth, but up in the sky. That's right. What might be speeding up this breakup process is the region's drying climate and brutal droughts. And that feels off, right? Usually tectonic plates move first and the climate changes afterward, but in East Africa, it might be flipped. The climate may actually be helping the plates pull apart faster. But first, let's look at what's really going on there. So, Earth's crust isn't one solid shell. It's made of giant tectonic plates, massive slabs of rock that never stop moving. They grind past each other, collide, slide under, climb over, or stretch apart. This motion is so slow, we don't notice it. But over long periods, those tiny shifts reshape continents, just like what's happening in Africa. For about 30 million years, the Arabian Plate has been moving away from the African Plate. That slow pull split the land. The seawater rushed in to fill the gap, forming the Red Sea and the Gulf of Aden. And that's not the only breakup happening there. In Eastern Africa, the Somali Plate is stretching away from the Nubian Plate. This is opening up the East African Rift Valley, cutting right through places like Ethiopia and Kenya. The region where these plates meet has a name. It's a triple junction. But in this case, they aren't crashing into each other. All three tectonic plates are diverging. When that happens, the crust gets pulled in different directions at once, like fabric being stretched from three corners. It weakens, thins out, and cracks open. They're pulling apart at different speeds too. The Arabian Plate is moving away from Africa at about an inch per year. The two African plates are separating more slowly, roughly between half an inch and 0.2 inches per year. And as they open that gap, hot material from deep inside Earth rises up and hardens, creating brand new seafloor along the split. I know, a few inches per year sounds ridiculously slow, but what makes this event so fascinating is that we're watching it happen in real time. We can actually see Africa slowly breaking apart, and it's terrifying. Back in 2005, a 35-mile long rift that opened up in the Ethiopian desert. The crack is 20 feet wide in some places, which is roughly the size of a shipping container. This is just one example of how active the region really is. From space, satellite images show valleys and rifts slowly widening over time. And down on the ground, people are posting videos of places where the Earth has already split open, leaving big cracks and gaps. Roads, houses, even schools are getting torn apart. The whole area keeps shaking from earthquakes, and the volcanoes are very active. What I mean is, even though this splitting process is super slow, we can actually see it happening, and it's unstoppable. Experts believe this crack in the East African Rift Valley will become a gateway. Waters of the Indian Ocean will eventually invade the valley and fill the growing gap. That will help pull the land apart even more, and eventually it'll create a brand new ocean. And we know that can happen because Earth has done it before. That's exactly how the Atlantic Ocean formed about 180 million years ago, when South America and Africa pulled away from each other. If the East African Rift keeps opening up, parts of Eastern Africa, Somalia, Kenya, Tanzania, Mozambique, and a big chunk of Ethiopia could one day break away from the rest of the continent. That means countries like Zambia and Uganda could actually end up with brand new stunning coastlines. But don't pack your swimsuit yet. Unfortunately, none of us will be swimming in the waters of this future sixth ocean anytime soon. Scientists estimate the full split would take about 5 to 10 million years. That's basically forever in human terms. But in Earth terms, it's surprisingly fast, almost like record speed. Now, scientists are trying to figure out why it's happening so fast. I mean, faster than it should. And here's a new intriguing possibility: a drying climate. One of the biggest clues starts right here at Lake Turkana. This lake in Kenya is about 19 miles wide and it's up to 400 feet deep in some places. But that's nothing compared to more than 5,000 years ago, when the lake level was up to 500 feet higher. Back then, the continent was going through something known as the African Humid Period. It was a time when Africa was wetter than it is today, and the Sahara wasn't a desert at all. It was green, wet, and full of lakes, rivers, and vegetation. But since then, the whole region has shifted into a much drier phase. So researchers took sediment samples from the bottom of Lake Turkana to figure out past water levels and how sediment washed into the lake over time. And while they were doing that, they noticed something else. Those sediment layers preserved lots of tiny faults and even the fingerprints of ancient earthquakes. Wait, wow! That means Lake Turkana might not be a simple lake. It could actually be one huge crack in the earth that eventually filled up with water. In other words, it could be a direct result of this whole rifting process. And now scientists think the same thing might be true for other deep, narrow lakes in the region, like Lake Malawi along the Tanzania-Mozambique border. So, scientists came up with a wild theory. What if these lakes are helping split Africa apart faster? Okay, maybe the theory isn't that wild. After all, water can indeed affect tectonic plates. For example, when glaciers melt and disappear, all that weight is removed, and the land underneath slowly pops back up, kind of like bread rising after you take something heavy off of it. That's called isostatic rebound, and big amounts of water can do the opposite. They press down on the crust, which can also affect things like faults and earthquakes. At Lake Turkana, something interesting shows up in the data. After the African Humid Period ended, the faults around the lake started moving faster, by about 0.007 inches per year. I know, that's a lot of zeros. But over thousands of years, that extra push can add up. And it could help explain why earthquakes might be more common in the region today than they were around 8,000 years ago. The study then ran computer simulations and found two likely reasons the shaking and fault movement sped up. First, there's less water pushing down on the ground. With that weight gone, the faults can slide more easily, like loosening a vise that was squeezing two pieces of wood together. Second, there's a volcano on an island on the south side of Lake Turkana. Deep underground, it has a pocket of hot, molten rock. When the lake level dropped after the African Humid Period, the pressure on the earth below eased up, like taking the lid off a pot. That lets the rock underneath melt a bit more. The extra melt flows into the volcano's magma chamber, swelling it up like a balloon. And that extra pressure can jolt nearby faults and trigger more movement. So yeah, drought and falling lake levels could be speeding up the splitting process. But it's not like the climate is creating the rift from scratch. It's more like the ground is already under tension, and the climate is giving it a little extra push. The real reason Africa is breaking apart might be related to something called superplume, an enormous column of scorching hot rock rising from deep inside the earth. Think of it like a balloon underground that's slowly filling up. As it pushes upward, it puts pressure on the crust above it. Over time, that pressure weakens the crust and slowly cracks it apart. And even though none of us will be alive to see the final result of this process, it's still amazing to realize that we're watching a continent split, almost in real time. The floor is lava! Haha, just kidding. But honestly, it's kind of falling apart. You might not feel it yet, but a huge part of North America has already lost 37 miles worth of rock from its foundation. And no, this isn't about earthquakes or giant sinkholes. It's about the continent losing pieces of the very thing that keeps the ground from wobbling around like a bad carnival ride. A team of researchers has just dropped a geological bombshell. Part of North America's ground is thinning out like a very sad, very slow ice cream drip. How do they know? They basically gave Earth a high-tech full-body MRI and created 3D maps showing how rocks once considered indestructible are now melting away into the planet's guts, like an upside-down cheese pizza inside an oven. But to really understand this mess, you first have to meet my old friends, Cratons. Cratons are like the roots of the continents. They're thick, tough, and ancient. We're talking billions of years old. These bad boys survived meteor impacts, supervolcanoes, and even the tectonic movement of plates. If the plates got into fistfights, for example, you can bet we would see mountain ranges being born. If they got a divorce, drifting apart from each other, then a whole new ocean would be born. All of these things leave scars on the surface of Earth, but the Cratons seem to always remain unfazed, like the cockroaches of geology. And since a Craton can basically get punched in the face and feel nothing, scientists always assumed these things were nearly indestructible. But then, a group of researchers took their fancy machines to the test and realized that, wait, the Cratons are falling apart? How? Enter the Farallon Plate, a really ancient tectonic plate that started to slide under North America's major plate over 100 million years ago. This is a pretty normal process, actually. It's called subduction, and it's how Earth recycles rocks and keeps itself from overheating. This subduction thing has been happening for so long that, by now, the Farallon is almost 400 miles away from the Craton, sitting pretty chill at the lower mantle, weirdly close to the outer core of our planet. But the Farallon has been causing trouble, like that one roommate who moved out but keeps leaving weird stuff in the fridge. You see, as it sinks, it tugs on the bottom of North America's foundation, stretching it out and causing pieces to fall off into the deep mantle. And if that wasn't enough drama, the sinking Farallon has also leaked water and carbon dioxide into the surrounding rocks, making the Craton even softer and easier to shred apart. Thanks, Farallon. Very cool of you. By studying hundreds of earthquakes across thousands of monitoring stations, scientists have confirmed the story. Big chunks of continental material are dripping downward, thinning the Craton by as much as 37 miles. That's more missing rocks than can fit into a milk carton. Sounds dramatic, right? But don't worry. This is happening at a snail's pace. It'll take millions of years for anything noticeable to happen. Your great-great-great-great few grandkids from the distant future might still be standing on solid ground. But don't get too comfy. This thing may not be an urgent problem, but there's another type of sinking that's happening faster than you can say, "Help." Here's the thing. By 2050, at least 32 major cities in the US, including New York, Baltimore, and Charleston, could be partially underwater. And guess what? This one is mostly our fault. Scientists noticed that since 2007, some cities have been sinking into the ground between 0.04 and 0.08 inches every year. Charleston, in South Carolina, is pulling ahead in the worst way possible, sinking 0.15 inches annually. Sure, these numbers sound tiny and a bit ridiculous, but Charleston is barely 9 feet above sea level. And a little sinking goes a long way when the ocean is breathing down your neck. On really bad flood days, people there have to abandon their cars and basically swim home. This whole phenomenon is called land subsidence. And when you mix sinking land with rising sea levels, you get a disaster cocktail of flooded streets, salty farmland, ghost forests, and a lot of very cranky homeowners. And it doesn't stop with just homes. Infrastructure like bridges, roads, airports, and power plants, all things we rely on daily, are also at risk of serious damage. Flooded electrical grids and sunken highways could cause billions more in economic losses and create major safety hazards for communities. Now, let's be fair. Not everything is humanity's fault. Some of this trouble dates all the way back to the Ice Age. About 12,000 years ago, massive ice sheets covered the northern US. They were heavy, like seriously heavy. The weight pushed the land down, and when the ice melted, the ground didn't just pop back up like a trampoline. Instead, it started playing a weird game of geological seesaw. The places that were squished started rising, and the places that weren't got pulled down. This whole process, called glacial isostatic adjustment, try to say that 3 times fast. But of course, humans found a way to make it worse. Groundwater extraction is a major culprit. Think of it like pulling the stuff out of the mattress. After a while, the whole thing just sags. In places like California's Central Valley, the land is dropping by up to 8 inches a year because we keep pumping out water during droughts. In cities like New York, the problem isn't just water. Skyscrapers themselves are making it worse. Yep, turns out if you stack millions of tons of concrete and steel onto soft ground, it tends to flatten. And in case you're wondering, the total mass of New York City's buildings is around 1.68 trillion pounds. That's about the same as 3.5 million statues of liberty piled up. With so much weight concentrated over a relatively small area, the underlying soils have no choice but to compress over time. And if you thought it couldn't get messier, think again. We've been building dams, which stop rivers from delivering fresh sediment to coastal areas. That sediment is kind of like Mother Nature's way of fluffing the ground back up. Without it, coastal lands are compacting like an old sponge. Plus, when wetlands are drained for agriculture or construction, the peaty soil dries out and collapses. Honestly, it's like the ground just can't catch a break. Scientists also noticed that the areas that used to be lush wetlands are now among the fastest sinking spots in the country, especially along the Gulf Coast. Louisiana, for example, is losing about a football field of land because of this mix of subsidence and rising seas. So what's the end game here for us regular people who just want to live above sea level? Well, it's not looking great. Ghost forests, which are basically drowned woodlands, are popping up. Farmland is turning salty and unusable. And even sunny day flooding, where streets flood without any rain, is becoming a thing. Yikes! Meanwhile, over on the West Coast, California is not exactly winning either. San Francisco and Los Angeles are both sinking, which means that rising sea levels could hit them twice as hard and twice as fast. In some places like the Palos Verdes Peninsula, the ground has been sinking so fast, people over there might as well live like moles. So, is America turning into the next Atlantis? Probably not next week, but without serious action, like cutting back on groundwater pumping and planning smarter cities, at least 500,000 people are in serious danger. And the housing damage could easily rack up a jaw-dropping $109 billion by 2050. In the end, while North America isn't about to sink like a poorly made souffle, it's definitely showing some cracks in the crust. So maybe let's ease up on groundwater pumping, rethink how and where we build, and invest a little more in keeping our feet dry. After all, if the floor really does become lava someday, we're gonna wish we had at least fixed the leaks first. For eons, the Red Sea has separated the continents of Asia and Africa. They're close enough to wave at each other, but far enough that moving between them requires planning. Ferries do the job, but it's time for something better. That's why engineers have envisioned an ambitious mega project of tunnels and bridges that will not only link the two continents, but also reshape the region forever. Millions of years ago, the Arabian landmass slowly drifted away from Africa, opening a watery scar that we now call the Red Sea. This place is famous for its crystal clear water that looks filtered even when it isn't, as well as for coral reefs that seem to be painted by an overachieving artist. Let's zoom in on one specific location, the Strait of Tiran. Every ship headed toward the upper ports squeezed through this one busy hallway. On the one side is Egypt, the Sinai Peninsula, rugged, golden, and sprinkled with resort towns. On the other side, it's Saudi Arabia, the Tabuk coast, where quiet desert hills stroll right down to neon blue water. The distance between them looks tiny on a map, almost like someone forgot to connect the lines. That's because the strait is only about 8 miles from peninsula to peninsula, close enough that on a clear day you can sometimes see the opposite shoreline. It's a busy gateway, and it's the exact gap designers want to turn into a direct road and rail link. So what are they actually trying to build? The idea is to create one continuous route between the Sinai Peninsula and the Tebuk coast. Engineers are still deciding whether it should be a bridge, a tunnel, or a hybrid, the combination of two. The problem is under the water. Near the shore, the bottom is shallow enough to support strong columns, but as you move farther out, the seabed drops quickly until it reaches about 900 feet. It's almost like walking off an underwater cliff. That sudden plunge is too deep for standard bridge supports. The design has to adjust to the landscape instead of forcing one shape across the whole gap. If they go with a bridge, the builders would place huge steel tubes called caissons on the seafloor. Think of them as giant metal buckets. Once they're in position, the water gets pumped out so crews can build a dry foundation inside. Concrete turns that space into a pillar rising from the seabed. The floating cranes drop long road sections between those pillars like puzzle pieces. It works well in shallow areas, but anchoring becomes difficult in deep waters due to high pressure, soft ground, and strong waves. Tunnels avoid this by going under the problem, literally. Crews can send tunnel boring machines called worms, or they can build submarine-sized tunnel segments on land and sink them into place. It's the same trick used in the Hong Kong-Zhuhai-Macau megalink, which proves it works even in busy, deep water. Now, people might look at the map and think, 8 miles? That doesn't sound so bad. In reality, it's nothing like tossing a giant tree trunk over a river and calling it a bridge. Cars, buses, and trains need those long, slow, friendly ramps that don't feel like a roller coaster. By the time you build those ramps on both sides, the whole thing could stretch to nearly 20 miles. That puts it in the same club as giants like the Chesapeake Bay Bridge Tunnel in the US or the King Fahd Causeway between Saudi Arabia and Bahrain. But it's not just the scale or unpredictable seabed that makes this intercontinental project challenging. There's also the climate. Temperatures regularly pass 100 degrees Fahrenheit. Concrete dries faster than planned, so crews have to cool it or work in shorter windows. Steel stretches in the heat just enough to make precise work annoying. And workers themselves cannot stand in direct sunlight for long without feeling like a baked potato. On top of that, the salty sea air chews through metal quicker than most people expect, so the whole structure needs tough protective layers and regular checkup. If this project gets the green light, you're looking at a timeline of several years. A good comparison is the Øresund link between Denmark and Sweden. It's only about 10 miles long and still took around 4 years to build, in an environment that is much easier to handle than the Red Sea. Then there's the price tag. Early numbers land around $4 billion, but that feels more like a starting guess than a final bill. If they run into problems, that figure will almost certainly climb. There's also one other problem that must be brought up: swimming right under the surface. The Strait of Tiran is home to dolphins, rays, sea turtles, and even sharks, including harmless reef sharks that glide around like they're protecting the beautiful, colorful corals below. These reefs aren't just decoration, they're some of the healthiest in the entire Red Sea. Scientists say that in parts of the northern Red Sea, some corals tolerate higher temperatures than many others around the world, which makes these reefs especially valuable from a climate resilience perspective. That means even a single mistake during construction could cloud the water with sediment, and that alone can smother corals like dust settling on wet paint. The same goes for noise, drilling, and ship movement. Reefs can't exactly move away if annoyed like fish can. Once they're damaged, it can take decades for them to grow back. That is, if they grow back. To avoid that, planners have to build in ways that keep the water as clear and calm as possible. Construction zones may need silt curtains to stop sediment from drifting away. Heavy equipment might have to avoid areas with dense coral clusters. Some sections could lean more toward tunnels instead of pillars to leave the seabed undisturbed. Every decision has to match the underwater map, not just the one on land. On top of that, the whole project would need constant supervision from scientists and inspectors. They would have to check how cloudy the water becomes and how marine animals behave during the work. If something looks off, the only responsible move is to slow down or change the method, instead of just rushing to finish faster and leaving the reef to pay the price. But if everything finally clicks into place, the payoff is massive. Right now, if you decide to skip the ferry and stay on land, the map punishes you. You have to loop all the way around the top of the Red Sea, through other countries on a drive more than 1,000 miles. All of that just to cross a stretch of water that is only a few miles wide at its narrowest point. It's like walking around the entire block just to knock on your neighbor's door. A permanent link would change this. Travel time drops, ports on both sides become easier to reach, and a drive from Africa to Asia suddenly feels as normal as crossing a long highway bridge. Not to mention the coolest part, which would be the view if they decided on the hybrid version. You begin your journey on the Sinai side, with the desert behind you and the Red Sea ahead. Instead of waiting in a ferry line, you roll onto a rising ramp while the water glimmers below. The road dips into a tunnel under a busy shipping lane, and before long, you're back in the sunlight on the other side, now on a different continent. The train version could feel even smoother. You find your seat, the doors close, and the train glides toward the crossing without any stop-and-go traffic. It slips into its own tunnel section, runs quietly under the sea, and pops back up on the Asian side before you have even finished scrolling your feed. For tourists, that could mean more resorts, more quick weekend trips, and a brand new Continental hop that becomes a must-try experience. For delivery trucks, every hour saved is money earned. Even local towns would feel the change. They'd get more visitors, more trade, and bigger profits. A link like this doesn't just connect land, it connects economies, ports, and everyday life. And that's a giant opportunity, as long as the underwater world stays protected.
So it turns out that you can't drive between South America and North America, and there's a simple reason for that. There are no roads connecting the two continents, not even a rudimentary one. Technically, you could try your luck crossing on foot, but let me tell you, that would be a huge mistake. The region that connects the two continents is called the Darien Gap. It stretches across southern Panama's Darien province and the northern part of Colombia. The only land route there is a 60-mile jungle trek. Crossing it can take anywhere from 3 to 10 days. It depends on weather conditions, how much you're carrying, and honestly, just pure luck. Chance plays a big role here, because this isn't some chill, relaxing nature walk. It's a harsh, extreme environment, known for being completely isolated and one of the most dangerous places on Earth. Still, people seem to forget that and go there anyway. Every year, the number of people crossing just keeps growing. In 2014, fewer than 10,000 people crossed the gap. In 2023, that number increased to 520,000. Now, you might be wondering, what are so many people doing in the middle of the two American continents, risking all that danger? Well, that's because the Darien Gap has become a route for refugees migrating to North America. But to get there, they face all kinds of dangers, from insect bites and infections to serious fractures. We're talking about a no-man's land. Since there are no police stations, immigrants must also watch out for thieves. Along the way, they have no choice but to rely on and support each other. Most people start the crossing with at least a tent or tarp, rain boots, water, and some food. But these things get heavy fast, and people normally can't carry enough supplies for the entire journey. At some point, people start drinking river water to avoid dehydration. But the water's full of bacteria and dirt, so it causes intestinal issues. And if things get serious, there's no medical help there. To make this whole scenario even worse, the temperatures are brutal, often hitting over 95 degrees Fahrenheit. Now, a small subset of people who venture through the Darien Gap are hardcore adventurers and travelers looking for a survival experience in the jungle. But this region is no place for a relaxing vacation. A group of tourists who went there in 2023 ended up getting jungle rot, a fungus that affects the feet. The situation got so bad that a woman had to be carried out by the group on the last day because she couldn't walk. No matter how prepared people are for the Darien Gap, in the end, survival mostly comes down to luck. Out there, travelers won't find cities with solid infrastructure where they can crash at a hotel and gear up for the next day. In some spots, they might stumble across basic camps right in the jungle. These camps might offer wooden platforms for tents, bucket showers, toilets, and even plates of chicken and rice. But it all comes at a price. Wi-Fi, for example, might cost $2 an hour, and that seems like a pretty good deal, considering there's no cell phone service on the trail. They pretty much lose all contact with the outside world. Now picture a dense rainforest with steep, muddy terrain. The hiking trail is littered with boulders and tangled with vines, like nature's own tripwires. It climbs sharply over a mountain, becoming a serious challenge even for someone in good physical shape. The area also gets constant heavy rainfall, which can lead to landslides, flash flooding, and extremely muddy conditions. The situation gets so intense that even the t-shirts and faces of those who make the crossing end up covered in mud. They'll also have to cross a lot of fast-moving rivers. A Venezuelan dad who recently went through the area with his 2 kids said their sneakers ripped apart on the very first day. That's how powerful the rivers can be. And they're deep, too. Sometimes the water reaches all the way up to their shoulders. But the dangers in that area aren't recent. For centuries, the Darien Gap was thought to be impossible to cross. The first Europeans who ventured into Latin America saw it as kind of a jungle training school. They totally knew about its dangers, but still, many adventurers tried to make the crossing in the years that followed. In 1854, for example, an expedition disappeared for 49 days in the jungle, battling starvation and exhaustion. Then again, in 1870, a group of 100 men set out to cross it. Even though they were well prepared and carried cutting-edge equipment for the time, they still suffered tremendously during the journey. They had to rely on incredible resilience to survive the challenge. Over the years, people who ventured in often ended up passing away from hunger, thirst, and even drowning in rivers. They also faced the risk of being attacked by dangerous animals like jaguars, white-lipped pecaries, and the fer-de-lance, a fast, irritable snake that is one of the most venomous out there. The area is also swarming with mosquitoes, which can spread serious health problems. Leaning against trees to rest can also be risky. This jungle is full of spiked chunga palm trees, which are covered in long black spines up to 8 inches long. Unfortunately for us, these spines are covered in all sorts of bacteria. Just brush against a chunga, and you could end up with infected wounds. And yet another danger is getting lost in the dense forest and never finding your way back to safety. These days, though, this risk is a lot lower. Some people have mentioned color-coded markers that help guide travelers and keep them from going the wrong way. If they see blue or green fabric tied to trees, it means keep walking. But if they spot red fabric, that's a sign they're going the wrong way and need to turn around quickly. Since there are so many dangers, why not just build a road through the Darien Gap? While it might seem like a good idea, building a road connecting Panama and Colombia isn't really that simple. The Darien Gap has a humid climate, tough terrain, and constant rainfall, which means any attempt to build a functional road would be highly challenging and super expensive. Even though there have been previous attempts to fill in the gap. See, there's a huge road system called the Pan-American Highway, which stretches all the way from Alaska to the southern tip of Argentina. Nowadays, this highway hits a roadblock right at the Darien Gap. But it wasn't supposed to be like this, as the original idea was for the road to go through there. Leaders from Latin American countries tried to make this plan happen in the 70s, and then again in the 90s. But a lot of people were against it, mainly because they wanted to protect the local communities and the rainforest. Since the Darien Gap is mostly untouched by humans, it's one of the most biodiverse places on the planet. It's believed that 1 in 5 species are endemic to the region, meaning they only exist in that specific area, like the Darien pocket gopher and the slatty slender mouse opossum. A road would have really damaged the ecosystem in the area, so the plans were scrapped. Eventually, an alternative was created to travel by sea. At least 2 companies started a ferry service connecting the 2 countries. However, the business wasn't profitable, and they ended up shutting down. Not long ago, Panama decided to close the Darien Gap route. Now they're sealed off with barbed wire fencing. It might just be a matter of time before other routes are created. But if you are an adventurer looking to visit South America, it's probably not best to wait for that. Traveling by plane to Colombia will always be a much safer option. Consider South America and Africa. Don't they kind of look like they fit together, like puzzle pieces? Well, they actually did. But about 130 million years ago, South America was like, bye, and slowly started drifting away. These days, it's around 1,800 miles from Africa, and it's still on the move. Every year, the continent shifts a little more toward the Pacific Ocean. So, how's that even happening? Tectonic plates are constantly moving. That's what makes the Earth's surface shift over time, going from this to what we see today. But those movements happen so slowly that you and I can't see them go. So, no, Brazilians or Chileans aren't out there feeling their continent inching westward. But the numbers don't lie. South America is moving, and apparently all it wants is to get as far away as possible from this massive underwater mountain range called the Mid-Atlantic Ridge. But what exactly is pushing the land toward the Pacific Ocean? It is the heat inside our planet. Way, way down beneath the ocean, there are cracks in the Earth's crust, and magma, super hot melted rock, rises up through those cracks. When that happens, the magma cools and hardens into solid rock. Over time, this process might build underwater mountains, like the Mid-Atlantic Ridge. And as more new crust forms, it begins to push the older crust out of the way. In the process, tectonic plates and the continents riding on top of them get pushed along. Now, on the other side of South America, over by the Pacific, there is the Nazca Plate. It's heavier and it's moving eastward. Since it is denser, it is sliding underneath the South American plate. This entire process is called subduction, and it's happening at a rate of about 3 inches per year. By the way, the collision between these 2 plates is what's behind all those breathtaking volcanoes scattered throughout the Andes, and it's also making the continent move. So, if everything goes according to plan, projections show that South America will end up more centered in the Pacific Ocean in the future. But some models suggest something way crazier. Before we get into that, though, we need to clear something up. Why on earth isn't Africa following in South America's footsteps? I mean, shouldn't it be drifting west too? Well, not quite. Africa is doing its own thing, because it sits on the African plate. So the Mid-Atlantic Ridge is located between those 2 continents, and just like it pushes the South American plate, it also pushes the African plate, but in the opposite direction. It's like this ridge is trying to split up 2 ex-besties, But there's more. Africa is also being influenced by the East African Rift. That's one of those massive cracks we talked about earlier, but it's happening on land, which makes it extra dramatic. This is what's causing the continent to slowly split apart. It's a long story, but let's just say the rift is pulling Africa in more directions than South America ever had to deal with. Okay, now it is finally time to talk about that crazier thing that might happen to South America and everything around it in the future. Theory number 1. It could break away from North America. I know, super dramatic, but don't panic. We're talking hundreds of millions of years from now, and I won't be around. You see, both continents are moving in the same general direction, but at different speeds. The North American plate is cruising along at about 1 inch per year, while South America is moving a bit faster. So even though they're heading the same way, they are not keeping pace. Over time, as the Atlantic Ocean continues to widen and the Pacific keeps shrinking, all this tectonic movement could eventually pull the Americas apart. Theory number 2. Marine life could go through some major changes. Right now, the Americas act as kind of a giant wall between the Atlantic and Pacific Oceans. Because of that, sea animals have evolved differently on each side. Take the green sea turtle, for example. The ones living in the Atlantic tend to be bigger and lighter in color. Meanwhile, their Pacific cousins are usually smaller and darker. But if, one day, there is no land blocking these two populations from mixing, they would end up with brand new migration routes, new nesting spots, and a lot more overlap in their territories. Now, multiply that scenario by hundreds of other species, and things could really get shaken up. We're talking about new interactions, unexpected competition, and maybe even the rise of entirely new species. Alright, theory number 3. America might meet Africa again. Right now, the Mid-Atlantic Ridge is busy creating a new seafloor, and because of that, the Atlantic Ocean is slowly getting wider. But in about 125 million years, scientists believe that process could come to a stop. Instead of the seafloor spreading apart, the ocean floor might start getting pulled under the continents. When that happens, the Atlantic will stop growing and start shrinking. And the water section between South America and Africa is likely to be the first part pulled beneath the land. That means the Americas and Africa could meet again. And when that happens, border countries could turn into super shaky places, with earthquakes happening all the time and brand new volcanoes popping up left and right. The eastern United States would no longer be known for the peaceful green slopes of the Appalachians, but for snow-covered giants that occasionally spew lava and ash, more like the Cascade Range out west. Countries would end up with totally new neighbors. Brazil might line up with Nigeria and Cameroon. Uruguay could be sitting right next to Angola, and Argentina might be sharing a border with South Africa. So if these two continents really do merge, how intense would that be? Well, for starters, this new supercontinent would instantly become the biggest one on Earth, about 1.5 times the size of Asia. And chances are, a brand new mountain range would form right where the continents meet, creating a natural border between nations. Being part of the same massive continent could make a lot of things way easier. For one, tourism could totally take off. People traveling between countries by land without needing pricey plane tickets could be a game changer. But it wouldn't stop there. Other types of economic activity could get a major boost too. Now on one side we have South America, which already produces and sells a wide variety of foods, from wheat to bananas, beef, cocoa, soybeans, hey, you name it. On the other side, there is Africa, exporting things like textiles and clothing. That alone would make them a super powerful bloc when it comes to trading raw goods. But can you name another important thing these two continents have in common? Yep, petroleum. Countries in South America, like Brazil, Venezuela, and Colombia, are major oil exporters. And over in Africa, you've got Nigeria, Algeria, and Libya doing the same. Now, can you see just how powerful that kind of union could be? Meanwhile, let's talk about animals. These two massive lands coming together could lead us to wild meetups, like a capybara sharing space with a Nile crocodile, or a sloth seeing a hyena from the top of a tree. This could even lead to new animal hybrids showing up, like a cabby crocodile or a sloth hyena. Okay, those weren't the cleverest names, and honestly, these animals wouldn't be able to mate or even wouldn't want to. But you get the point, right? It's not all positive, unfortunately. New species showing up could become predators, competitors, or even parasites to the native plants and animals. It would take a long time for things to settle into a new balance in those border regions. But honestly, no one really knows how long it would take. The only thing I do know is neither of us will be around to see it, which is okay.
There's a stretch of water that even the most experienced explorers fear. No matter what season you choose to cross it in, you risk meeting face-to-face with waves that can reach as tall as the Hollywood sign. I'm talking about the Drake Passage, the waterway connecting the Pacific Ocean to the Atlantic Ocean, stretching from Cape Horn at South America's southernmost tip to Antarctica's South Shetland Islands. It's about as wide as the distance from London to Berlin and takes up to 48 hours to cross. Some sailors compare getting on the other side to going to the moon. That's how challenging it is. Even the man who discovered it, Sir Francis Drake, never sailed these waters because they seemed too dangerous to him and opted for a calmer, although longer, Strait of Magellan. The passage took the lives of around 20,000 sailors and over 800 ships. Tourists who want to see Antarctica cross the Drake Passage on a regular basis, although it's still often called the world's most terrifying ocean crossing. The Antarctic Peninsula, where travelers go, isn't really part of Antarctica itself. It sticks out and points towards South America like two fingers almost touching it. The water gets squeezed between these two land masses, making strong ocean currents. The passage is part of the Antarctic Circumpolar Current, the largest ocean current on Earth. The water rushes through the passage at a speed between 95 and 150 million cubic meters per second, which makes it rougher. And then there are winds that usually blow from west to east and are very strong between 40 and 60 degrees latitude. That's why those areas are called the Roaring Forties, Furious 50s, and Screaming 60s. Land slows down winds, which is why storms hitting Ireland and the UK get weaker as they move east. But Drake's latitude is the only place where winds can blow all around the Earth without being stopped by land. So they keep getting faster. These strong winds turn into huge waves that can hit ships really hard, normally around 13 to 16 feet tall. They're much higher than waves in the Atlantic. Drake Passage also has underwater mountains that you can't see. The huge current squeezes through this narrow passage and causes waves to crash against these mountains underwater. These internal waves create whirls that bring cold water up from the deep ocean. So it's not just rough on the surface, the water is wild all the way down. The first sailor managed to sail around Cape Horn and through the Drake Passage in 1616. It was a Dutch navigator, Willem Schouten, in 1616. But the most famous attempt to cross it was undertaken by Sir Ernest Henry Shackleton on his ship named Endurance. He and 27 of his men set off from South Georgia, aiming to reach Vassal Bay in Antarctica. But things didn't go as planned. On January 19, 1915, their ship got stuck in the ice. And by October, it began to sink. They camped on floating ice for 2 months before sailing lifeboats to a remote, icy place called Elephant Island. Shackleton and 5 men made a risky journey to South Georgia to get help. It took them 15 days to cross Drake Passage with hurricane winds. Finally, they arrived safely and organized a rescue for the rest of their crew. Scientists found the shipwreck of Endurance only in 2022, 10,000 feet below the water. In December of 2019, 6 fearless athletes decided to cross the Drake Passage by rowing a boat for the first time in history. It took them 12 days of non-stop rowing with a 90-minute rotation of rowers. They managed to do it, and it was probably the hardest possible way to cross the passage. The athletes mentioned it was cold, wet, and dirty, and the waves hit them like walls. The weather in the Drake Passage changes a lot, but ship captains can always see it coming and change their path. They will move the departure time to have a safety margin and not to get stuck in the middle of the passage in the worst possible conditions. Sometimes, the journey will be smooth and calm, and they call it Drake Lake. Other times, people on the ship will feel rough waves, which is called Drake Shake. Some experienced captains who often cross the passage say that the Drake Lake effect happens once in every 10 crossings, and they see the Drake Shake once or twice in every 10 journeys. A schooner or a kayak will probably not survive the journey among giant waves, but modest vessels and cruise ships have sturdy hulls and advanced stabilizing mechanisms. So, the journey isn't that dangerous anymore, but still, it's quite an adventure, especially if you're seasick. If you don't feel like risking it but want to travel from the Pacific Ocean to the Atlantic Ocean by water the fast way, the Panama Canal is waiting for you. People first started thinking about making a water path across Panama in the 16th century. Back then, a Spanish explorer found out that only a thin piece of land separated the two oceans. But it seemed impossible to build it because of the mountains and thick jungle, so the idea had to wait a couple of centuries. Finally, in 1880, France, led by the man who built the Suez Canal in Egypt, tried to make the canal. But the people who started the construction soon found out it was much harder than it looked on a map. The land in Panama was one of the toughest and most dangerous places to dig a big waterway. Workers had to literally move huge mountains in a jungle full of snakes, where it was really hot and rainy. During the wet season, heavy rain turned rivers into wild rapids and soaked the workers. Sometimes, they didn't see the sun for 2 weeks, and their clothes stayed wet all the time. Big rocks were falling, and tiny mosquitoes that carried malaria made people very sick. And then, an earthquake happened on top of everything. They were losing thousands of people. That's why France decided to abandon the project after 7 years. Then, the United States bought the French assets in the canal zone and finished it by 1914. It cost the US around $375 million. The 50-mile-long passage of water saves ships traveling between New York and San Francisco 7,872 miles. Around 14,000 ships use it every year and pay around $1.8 million in tolls. So it looks like it all paid off. Another challenging waterway in this part of the world is the Amazon River. It's around 4,300 miles long and flows through 3 countries with over 30 million people living in its basin. But there isn't a single bridge across it. The river has many marshes and soft soils, so engineers would need to build very long bridges and very deep foundations, which costs a lot of money. Building bridges over deep water is tough, but in other places in the world, engineers can use things like floating platforms to help. The river's path and water levels change a lot during the year. During the dry season from June to November, the river is usually 2 to 6 miles wide. But in the wet season from December to April, the river can become as wide as 30 miles. And the water level can rise by 50 feet. That's why they can't build floating bridges or pontoons. The riverbanks are made of soft dirt that moves and erodes with the seasons, and it makes things even harder. It would have to be an absolutely unique project to overcome all these challenges. Luckily, there's no pressing need for a bridge across the Amazon right now. The river mostly goes through areas that are sparsely populated, so there aren't so many major roads to be connected by bridges.
Take a look at Australia from space. Nothing unusual, right? But now, focus on the northern territory of the continent. If we imagine it through magnetic sensors, we notice, whoa, see that? An unknown strange thing that mirrors the outline of Australia itself. It looks almost the same, but smaller. It's like a twin of the continent hidden deep within it. But what is it? Volcanic lakes? Gold deposits? No, it's something far stranger. This is a magnetic anomaly. Yeah, you're probably confused, but let's find out what's going on with Australia. So, there are devices called magnetometers. They measure magnetic fields, and geologists use them for many things, including exploring the interior of our planet. The magnetic field comes from various metals and minerals buried deep underground. It travels upwards, and scientists' sensors detect it. One day, they equipped aircraft with these magnetometers and flew over the northern part of Australia. When they processed the data and identified a magnetic anomaly with clear geological boundaries, whatever lay in Australia's interior was emitting magnetic signals and followed the outline of the entire continent. And because these signals come from deep rocks, scientists think that valuable resources, including minerals and metals, might be hidden there. But beyond potential resources, what else does this tell us? Inside these rocks, there could be volcanic materials formed over 1.5 billion years ago, minerals that formed long before the dinosaurs appeared. This entire mass of material could tell scientists about our planet's history and how the Australian continent was formed. Okay, that sounds cool, but why are those changes in the magnetic field they detected called an anomaly? Why is it magnetic in the first place? And how does this magnetism work? To understand, we first need to grasp what Earth's magnetic field is. And this is one of the most amazing and mysterious things in the world. The magnetic field is invisible, yet without it, we couldn't exist. So, in simple terms, Earth's magnetic field is our protective blanket, shielding us from cosmic radiation, charged solar particles, and the solar wind. Without the magnetic field, our Earth would be like Mars, a barren desert where life most likely couldn't have emerged. But where does it come from? The magnetic field is generated deep within our planet, where molten nickel and iron create electrical currents. Combined with our planet's rotation, these electrical flows generate the magnetic field that protects us. In addition, minerals and metals inside rocks can produce magnetic fields too. But what exactly is this force? Take two magnets from your fridge and try to push them together. Feel that resistance? That repulsion happens because their magnetic fields are interacting. In some places, this magnetic field can be weaker, and in others, stronger. This means that deep within the planet, in those locations, there are geological processes happening that change the stable behavior of the magnetic field. These places are what we call magnetic anomalies. One of them lies beneath the northern part of Australia. However, the magnetic field is more than just a blanket. Thanks to it, many awesome things happen. For example, a compass needle always points north because the Earth's south magnetic pole is located there, attracting the magnet. Don't confuse the geographic and magnetic poles. The geographic North Pole is in the north, near the magnetic South Pole. It's not just humans who use the magnetic field for navigation. Animals can do it too, without any instruments or technology. Some animals sense the magnetic field, and this superpower is called magnetoreception. This ability helps animals during migration. That is, they know where north and south are. So when it gets cold, they can fly to where it's warm. For some turtles, magnetoreception helps them remember the location of feeding areas. Pigeons have a unique perception of the magnetic field too. In simple words, the magnetic field is also a giant navigation system for many creatures on Earth. Few people know, but we actually have a second magnetic field. In 2018, scientists published research describing how ocean tides create another magnetic layer. But why hadn't we noticed it before? Our main magnetic field, generated by the planet's core, is very strong. Its radiation extends into space and is easy to detect. The magnetic field from tides is almost 20,000 times weaker. How does this field affect the main one? What are its properties? Scientists continue to study these questions. Also, the magnetic field can control the brain. In 2017, scientists used magnetic fields to remotely activate brain cells in mice. Magnetic forces were directed at the parts of the mouse brain responsible for body movement. In this way, the scientists could make the rodent run, freeze, and turn around. But don't think this was done just for fun. Experiments like this can be very helpful for humanity. If you can make a small animal move, imagine what other changes might be possible in the brain. Improving psychological state, for example. Potentially, you could instantly switch from a bad, depressive mood to a happy one. This technology could help treat many diseases related to the brain and nervous system. You might think that such a technology could control you, but don't worry. Magnetic fields pass through your tissues with almost no effect. But then, how did they manage to control those mice? Scientists simply implanted tiny magnetic particles into the animals' brains. Under the influence of a magnetic field, these particles heated up and triggered the activation of neurons. But the coolest thing happens when the magnetic field collides with the solar wind, generating electrical currents and magnetic forces. At the moment, a true cosmic storm happens in the sky, and we see it in the form of beautiful auroras. Such storms are not only beautiful, but also destructive, as they can disrupt the operation of satellites and electronic devices. Sometimes this can lead to minor glitches in your GPS or internet connection on your phone. But there have been cases where magnetic storms were so massive, they led to catastrophic consequences. One of them occurred in 1859 and is known as the Carrington event. On September 1, 1859, an amateur sky watcher, Richard Carrington, noticed a sudden bright white flash on the sun. It turned out this flash was a massive ejection of plasma from the sun's upper atmosphere. About 17 hours later, part of this energy reached our planet and struck as a powerful storm. All telegraph systems at the time went down. The northern lights were visible not only to residents of northern regions, but also in the tropics. For many people who had never heard of or seen the northern lights, this was a real surprise. What must they have thought? The end of the world? Unknown forces from space? Many were undoubtedly shocked by the spectacle, but the real shock was inside major cities. Communication between telegraph systems was stopped. The world was plunged into an eerie silence. Sparks flew from telegraph machines, causing fires in some places. People couldn't send or receive important information. Fortunately, the consequences weren't too catastrophic. Communication technologies were just beginning to develop at that time. But what would happen if such an event occurred today? Many experts have estimated that the damage from a similar storm in the United States could reach up to $2.6 trillion. The entire internet would shut down. For a while, we would lose access to our messaging apps, our banks, our navigation systems. Contactless payments, airports, train stations, and much more would stop working. We would be cut off not only from the internet, but also from electricity for a long time. The entire planet would be plunged into darkness and silence. A global economic and humanitarian crisis would begin. It's hard to imagine the damage that AI would suffer. But don't worry, the good news is that storms like this happen roughly once every 500 years, and smaller ones about every 50 years. But these aren't precise forecasts, since it's quite difficult for scientists to predict the sun's behavior. Besides, we wouldn't just sit in shock after such an event, we would immediately begin dealing with the consequences. The impact on modern civilization from such a storm would be significant, but we would surely recover quickly. Australia feels like the safest place on Earth, geologically speaking. No megavolcanoes, no massive fault lines slicing cities in half, no constant earthquake alerts. It looks solid and unbreakable, but according to a brand new global stress map of Earth's crust, Australia is one of the most internally stressed pieces of land on the entire planet. It's not shaking or cracking yet, but it's quietly storing energy like a bent ruler about to snap. To understand why this is such a big deal, imagine Earth's crust like a giant jigsaw puzzle made of moving slabs called tectonic plates. These plates float on softer rock below and push, pull, or grind against each other. Where plates meet, earthquakes and volcanoes make sense. But stress doesn't just stay at the edges, it travels. It builds up inside plates too, like pressure spreading through frozen ice when you squeeze it. Scientists mapped over 100,000 real stress measurements from oil wells, rock tests, and earthquakes to see where Earth is being squeezed the hardest right now. When they laid all the data together, the map lit up like a warning sign, and Australia stood out. This shocked scientists because Australia sits far away from plate boundaries, which usually means stability. But instead of relaxing, the Australian continent gets squeezed from multiple directions by nearby plates, especially the Pacific and Eurasian ones. The stress doesn't release easily, so it piles up inside the crust, and then nothing moves. Until suddenly everything does. One of the strangest discoveries showed up in places like the Bowen Basin, where stress directions twist and rotate underground. That's bad news because unpredictable stress behaves like glass about to shatter. These rotating stress fields make it nearly impossible to say when or where cracks could form. It could be years away or tomorrow. And human activity makes it even riskier. Drilling deep into the crust for geothermal energy or injecting fluids underground can nudge these stressed zones just enough to trigger fault movement. This doesn't mean Australia is about to split in half next week. But it does mean the idea of geologically safe might be outdated. Scientists now think Australia could eventually fracture internally and form new fault systems where none existed before. What makes the new stress map different from older models is that it doesn't just explain past earthquakes, it helps identify future risk zones before anything breaks. Countries can use this data to decide where drilling is safer, where tunnels shouldn't go, and where infrastructure needs reinforcement. But even with all this data, we still can't predict the exact moment Earth will snap. Stress maps tell us where the tension is. They don't tell us when it gives up. But this idea of continents quietly tearing themselves apart isn't just theory. Africa gives us the clearest real-world example. It's slowly unzipping itself. So slowly that no human will ever wake up and see a new ocean where land used to be, but fast enough that scientists can actually measure it happening right now. Deep beneath East Africa, the ground stretches, thins, and pulls apart as if the continent is taking a deep breath and never fully exhaling. And over millions of years, that stretch could turn into an ocean. This whole process centers on something called the East African Rift System, or EARS for short. Think of it like a giant tear running through the continent, thousands of miles long, cutting through countries like Ethiopia, Kenya, Tanzania, and Mozambique. It's one of the biggest rift zones on Earth. A rift zone is exactly what it sounds like, a place where the planet's crust is being pulled apart instead of squeezed together. And Africa just happens to have one of the most dramatic examples anywhere on the planet. What's really happening is that Africa isn't one solid plate anymore. It's splitting into two massive chunks, the Nubian plate to the west and the Somalian plate to the east. These two plates are drifting away from each other at a speed that sounds laughable, just less than an inch per year. That's about the speed your fingernails grow. But give that process millions of years and suddenly continents don't look so permanent anymore. In 2018, photos of a giant split in Kenya went viral across the internet. Headlines screamed that Africa was splitting in half right now. It looked dramatic, but that moment didn't mean Africa suddenly broke overnight. That rupture was more like a surface ripple, a small local sign of a much bigger process that's been going on for around 25 million years. And if we could travel in time to 5 or 10 million years from now, we would probably see the crust thin enough for seawater to rush in. When or if that happens, East Africa would slowly peel away from the rest of the continent, and a brand new ocean basin would form between the two plates. Africa would lose its eastern shoulder, and maps of the world would need a serious update. As strange as that sounds, it's actually totally normal for Earth. The planet never stops reshaping itself. It just works on a timeline so slow that our brains struggle to process it. The continents we know today feel ancient and permanent, but they're basically temporary arrangements. About 138 million years ago, South America and Africa were locked together like puzzle pieces. You can still see it if you look at their coastlines. They match almost perfectly. East Africa drifting away will just be the next chapter in that story. Australia's story could follow a different path, but the physics are similar. Stress builds, rock resists, then the rock fails. And stress doesn't care about borders, cities, or how calm the surface looks. That's why scientists are so concerned about something called SH max, the direction of maximum horizontal stress. In simple terms, it tells us which way the Earth is squeezing the hardest underground. If that squeezing lines up with existing fractures, earthquakes become more likely. If it cuts across old faults, new ones can form. Turkey is another place where the stress map practically screams danger. The country sits where Arabian, Eurasian, and African tectonic plates collide. There's also a smaller Anatolian plate on which Turkey is located, and which gets squeezed westward like toothpaste, grinding against massive faults. The stress map shows SH max pointing in directions that load these faults perfectly. Now, researchers looked at ancient lava flows near one of Turkey's faults and realized they weren't random. Lava sheets once flowed smoothly across the land, cooled into solid rock, and then got pulled apart over time, like a snapped chocolate bar. That gave scientists a rare, clear snapshot of how continents deform from the inside out. To date the lava, the team used microscopic zircon crystals trapped inside it. These crystals work like natural stopwatches. They trap helium created by radioactive decay, and by measuring that helium, scientists can tell when the lava erupted and cooled. When they combine that with satellite images and remote sensing, the scientists managed to see Earth's slow motion movements. The Hayward Fault stretches more than 120 miles and is so massive that you can spot it from space. For years, scientists assumed it behaved like many of Turkey's dangerous faults, where land slides sideways past itself. But this new research flipped that idea on its head. The fault isn't sliding, it's slowly ripping open. The land on either side moves away from each other at less than an inch per year. That sounds tiny, but then again, over thousands or millions of years, that motion adds up to continents literally thinning and breaking. And since the fault sits where three massive tectonic plates meet, this matters way beyond Turkey. All this once again reminds us that continents don't just collide or slide. Sometimes they stretch until they snap. And places that look calm on the surface might already be under invisible strain, inch by inch, year after year, rewriting the map long before anyone feels the shake.
So a few years ago, in 2019, folks in Australia said they liked an old idea with a new twist, using extra floodwater from the north to help dry areas in the west and south. This plan got the name of the New Brainfield Scheme. It was based on an old idea from the 1930s. The idea was to catch floodwater from the north and move it to the south and west. But the original plan never actually happened. Over the years, lots of experts said it wouldn't work. They thought it was too expensive and too tricky to build, even though it could potentially help fix drought problems in dry parts of Queensland. The original idea appeared a long time ago, when an engineer named John Brainfield got a big idea. He wanted to take floodwater from rivers in northern Queensland and send it inland to Lake Erie, one of the driest spots in Australia. He planned to use dams, pumps, really big pipes, and even tunnels to transport all that water over the Great Dividing Range, a big mountain range in Australia. The biggest dam would have been called Hell's Gate, and Brainfield wanted it twice as tall as what it was originally planned. This way, pumps and gravity could help move the water over the Great Dividing Range. The water would then flow south and help irrigate farmland near places like Hughenden. It would change the weather, make it rain more, and turn the dry land into green farms. Eventually, it would reach Lake Erie, turning the desert into a green growing area. That way, Australia could grow more food, sell it to other countries, and make more jobs. He hoped that the area could turn into a food bowl for the country. For some time, people talked about the plan a lot. They loved the idea. They thought it could change how farming worked. And some even believed that nature had already planned for the land to be filled with water. Dry rivers and lake beds were just waiting to be used. They even said that rains fell on the wrong side of the mountains, and Brainfield's plan could fix that. But when the authorities looked into this idea, they found big problems, and the main one was that the plan would cost too much. Plus, there weren't enough scientists or engineers to do a full investigation. The land was too dry and harsh. No one was sure it would even work, like how much water would really get there. Plus, some of Brainfield's measurements were wrong, especially the dam heights. So, in 1947, they officially shut the project down, claiming that even if they built the project, it wouldn't be worth it. After all, even places next to oceans, like parts of Chile, still stay bone dry, so a big lake might not result in more rain. And still, in 2019, one political party brought the idea back with an updated version called the New Brainfield Scheme. They wanted to try it again, but with some changes to make it work better. Their plan included the following steps. Take water from the South Johnstone, Tully, Herbert, and Burdekin rivers. Store that water using a big dam called Hell's Gate Dam, but this time they wanted to make the dam twice as tall as in the original plan. Let the water flow through tunnels using gravity instead of using lots of pumps. Move the water under the mountains and into the Warrego River in southern Queensland. Use the water to grow crops in dry places south and west of Hughenden, a huge area even bigger than Tasmania, eventually turning it into a food bowl. At the same time, they didn't say how much the whole project would cost, but they promised to spend $20 million to let Australia's National Science Agency check if the plan could work. Those innovative ideas sounded good, but for over 80 years, loads of experts kept saying, "Nope, it won't work." Why? Branfield said his idea would cost £40 million back in 1941. That's about $3.2 billion today. But the new version of the plan might cost more than $15 billion and take over 10 years to build. Also, people who care about nature are worried. They explain that taking water away from where it usually goes could hurt animals and plants. It might let invasive plants and animals spread to new places. It might mess up rivers and oceans, where fish and other animals live. It could even hurt towns and businesses near the coast that depend on those natural water flows. Still, some people really believed in the idea and thought it was worth doing, especially to help farmers and fix drought problems. However, in 2022, the government decided to stop trying to fix the drought in western Queensland with the Branfield scheme. Experts looked closely at the plan and said it just wouldn't work. The problem? There's not enough water all the time to make it happen. Apparently, the new cost of the plan would have been over $30 billion. That's a huge amount of money. You could buy yourself a fleet of private jets and luxurious yachts, and more. So experts said you'd need lots and lots of water to spend that kind of money, but the water just isn't there. Now, instead of one huge project, they suggested doing smaller water projects closer to where the rain and waterfalls are. These smaller projects, called mini Branfield grids, would be in 4 places along the Queensland coast. Those little grids could share water when some places had more or less rain. Other scientists looked at the plan too, and they agreed. Even if things went super well, the Branfield scheme would still cause problems and cost way too much, while the mini water grids project looks more plausible. They think the dry parts west of the mountains will do better without the full-scale Branfield scheme. There are easier and cheaper ways to help those places grow and get water. So the big plan was dropped, and now they're looking at smarter, smaller ideas to help with water and farming. And the matter is quite urgent. Australia is a super dry place, one of the driest places people actually live in. When there's a drought, there's not much water around. That means farms don't grow as much food, and that can cause a lot of problems. In the future, droughts are likely to happen more often and be worse. That's why it's necessary to start getting ready now. Experts are working on something called the Drought Resilience Mission, trying to figure out how to deal with droughts better in the future. One of them looked at how much droughts actually cost Australia. His research shows that droughts can hurt a lot of things – farms, jobs, towns, and even the whole country. When there's no rain for a really long time, some towns can actually run out of water. That's called day zero. It's when the taps in people's houses get turned off because there's just no water left. In 2020, a town in Queensland called Stanthorpe hit day zero. About 50 other towns were really close too. When such a situation happens, the only way to get water is by bringing it in with trucks, and that's super expensive. Stanthorpe had to get around 20 trucks of water every day for a year and a half. It cost them about $800,000 every month. In the end, they spent over $14 million just to have water. Luckily, it started raining again and filled the dams back up. But the authorities are working on ways to stop this kind of thing from happening again. They want to help towns be ready so they never run out of water like that. Because drought just doesn't mess with water, it can also mess with people's health. When everything dries up, plants vanish and the soil gets loose. Then the wind picks it up and makes huge dust storms. Those dust clouds can blow really far, even into such big cities as Sydney. That's what happened in 2018. The air got so bad that kids, older people, and anyone with breathing problems had to be extremely careful. The dust ruined some crops and made different foods, even fruit, unsafe to eat.
The world's largest fence spans over 3,100 miles from Queensland to South Australia. If stretched out, it could easily connect London to New York. And if you'd walk next to it, you'd need 6 months to complete the journey. It wasn't built to safeguard the Australian border. Why would it, since Aussies are just surrounded by water? It wasn't meant to protect some important building either. Its purpose is to keep some animal species away from each other. It was back in the late 1800s when Australians started building parts of this fence. They wanted to create a barrier separating the lively, bustling part of the country where cities like Melbourne and Sydney thrive from the harsh, dry outback. They used wooden posts dug deep into the ground, linked up with wire mesh standing about 6 feet tall. Some parts of the fence even have a second electrically charged layer. To make sure this fence did its job, they added some red and white lights to help guard things even at night. A team of over 20 people work full-time to keep things in check here. And every year, local authorities chip in around $750,000 to keep the construction in shape. Why all this trouble? The main reason was dingoes. These gingery, wolf-like creatures are Australia's largest carnivore mammals, and they're also apex predators. They were causing a lot of trouble to local farmers, especially in southern Queensland, where they often go after sheep. For the most part, the fence has been doing its job okay, but it's not foolproof. Some dingoes still manage to sneak through. Other times, wild camels end up crashing into it. That's because Australia has quite a massive camel population roaming around. But this man-made solution did more than locals expected. They thought there would just be fewer dingoes within the fence, but fewer dingoes mean more kangaroos. And more kangaroos mean more competition with the sheep for food. It's not just the bigger species feeling the squeeze. The smaller animals and the greenery also went through changes. With all this competition in a smaller space, locals noticed less diversity in the plant life and small animals. The soil became less nutritious over time, affecting plant growth. Plus, the fence acts as a roadblock for animal migration and seed dispersal. Even the sand dunes are feeling the effects, with less grass cover to hold things together. When scientists looked at kangaroos on both sides of the fence, they noticed that the young pups inside were lighter and tinier on average. The outsiders had bigger feet and heads for their age, and it wasn't because they were eating a different diet. The kangaroos that were stuck sharing the land with dingoes had to bulk up faster to survive. On the flip side, those inside the fence took it slower because they weren't under the same type of pressure. These had to compete with a lot of other creatures for food, so a bigger size wasn't a priority anymore. Researchers are still not sure if this difference is a quick fix or a long-term gene adaptation. What about domesticating dingoes? Wouldn't that help? Many think dingoes were once pets in Australia, but it's not known for sure. These days, they're pretty wild, just like wolves, hyenas, or coyotes. Most of them don't need packs to survive and are solitary hunters with sharp instincts built in. So taming them isn't going to be easy. Still, taking down the construction is not an option for now. Australians are so strict when it comes to making sure dingoes are kept away that they even put laws in place for people who mess up with the fence. Leaving a crossing gate open can put people behind bars for up to 3 months. Damaging the fence can cost people 6 months' worth of their freedom. It wasn't the first time Australians thought a fence could help with animal issues. Before they needed it for dingoes, they experienced a serious bunny invasion. Cute as they are, rabbits were damaging the land used for farming, so locals thought of a 3-part fence. The first one stretched all the way from Ravensthorpe in the south to Pardue Station on the Pilbara coast. It was over 1,100 miles long, making it the longest unbroken fence globally at the time. All these bunny problems could have been traced back to a man named Thomas Austin. Back in 1859, when he first came to the land down under, he thought it would be a good idea to release a few rabbits into the wild, thinking it would add a bit of charm to the place. But since rabbits aren't native to Australia, they didn't have any natural predators at the time. They're also pretty adaptive creatures, needing just some grass for feeding. They reproduce at astonishing speeds too. A mama rabbit can have 4 litters a year, with as many as 5 bunnies each. Pretty soon, their numbers boomed. By the late 1880s, the bunnies had caused so much damage that local authorities came up with a proposal. They'd offer the equivalent of almost $2 million today to anyone who could come up with a solution to this long-eared problem. Nobody claimed the prize, But a commission did gather a bit over a decade later and came up with the fence idea. Maintaining those fences was complicated. They had inspectors keeping an eye, with each one responsible for a stretch about 500 miles long. There were also these boundary riders patrolling smaller sections, using bikes at first, then switching to camels or using camels to haul buggies. They even tried using cars at one point, but they couldn't handle the rough terrain and constantly had punctured tires. In terms of its effectiveness, well, by 1902, rabbits were already hanging out on the wrong side of the fence. That's why, 4 years later, they put up another one. It worked for a while, so much so that the local authorities didn't bother helping out farmers past that second fence with rabbit netting loans. Those caught between the two fences, however, still had a rough time dealing with rabbit trouble. Soon enough, rabbits spread even over fence number 2, and it was clear the solution didn't work. In some areas, even while the fences were being built, those sneaky bunnies found their way past them. To this day, the rabbit population still sometimes puts the Australian officials through rough times. The Dingo Fence may be the longest one, but it's not the weirdest. The aquarium fence in Turkey might take that prize. This 164-foot aquarium fence was built to make sure the expensive villa's ocean view would be visible from every one of its levels. These days, it gathers a lot of tourists from all over the world, eager to see the variety of fish it contains, and even the octopuses. Putting up a see-through structure wasn't hard. The real challenge was connecting the aqua fence to the Aegean Sea through a buried pipeline stretching across 13,000 feet of land. This ensures water constantly flows, keeping the aquarium clean and the fish happy. To make sure no one damages the delicate fence or steals any of the fish or two, the owner also invested in security. He installed a network of 17 cameras equipped with facial recognition. Visitors are free to look and take pictures, but step too close and you're likely to trigger alarms. Another one of those weird fences is New Zealand's bra fence. If you ever find yourself through central Otago, you might stumble upon a fence adorned with bras of all kinds of shapes, sizes, and patterns. Its story takes us back to 1999, when people in the area found 4 bras mysteriously hanging on the fence near Cardrona Valley Road. Some were a bit surprised, but then others started adding their bras to the decor. Some more bras appeared, and it became a must-see spot for tourists. Its popularity was so high that at times it caused traffic problems in the area.
Turkey is quietly tearing itself open, and no one noticed for decades. Scientists didn't just get a detail wrong, they misunderstood the entire motion of a massive chunk of Earth's crust. What they thought was sliding sideways is actually stretching apart, inch by inch, like the planet is slowly pulled in two. And once you see that rupture, you start noticing them everywhere. To understand why this shocked geologists so badly, picture Earth's crust like a cracked shell floating on something hot and squishy underneath. Those cracked pieces are tectonic plates. They move a few inches per year, which sounds tiny, but over millions of years, it reshapes continents. Turkey sits in one of the most uncomfortable places on Earth, squeezed between 3 huge plates: Eurasia to the north, Africa to the south, and Arabia pushing in from the southeast like an elbow in a crowded bus. For decades, scientists believe Turkey survived this squeeze by sliding sideways. This type of movement is called a strike-slip fault, which basically means 2 chunks of land grind past each other like hands rubbing together. Turkey has famous ones, like the North Anatolian Fault, which produces horrible earthquakes. That model felt neat and logical. Pressure comes in, land escapes sideways. Problem solved. Or so everyone thought. But geology doesn't always follow neat models made up by humans. There is a long fracture running beneath salt flats and farmland under central Turkey. It never behaved like the dangerous sideways faults, so it got less attention. Then researchers from Craton University decided to look closer. And instead of watching earthquakes, they watched lava. Ancient lava. Lava that flowed across the fault thousands of years ago, cooled into solid rock, and later ruptured apart.
There are tiny crystals called zircons inside that lava. They're basically nature's stopwatches. Zircons trap radioactive elements that decay in a predictable rate, so scientists can tell exactly when the lava cooled. When they matched lava chunks on opposite sides of the fault and measured how far they drifted apart, the team managed to reconstruct how the fault was moving over thousands of years. It turned out that the fault wasn't sliding sideways at all. It was slowly and steadily pulling apart, just a fraction of an inch per year. That's thinner than a grain of rice, but over geological time, it's massive. This type of fault is called an extensional fault, which means the crust stretches until it thins and breaks. In simple terms, Turkey isn't just being squeezed, it's being torn open. And as if that wasn't dramatic enough, the story gets worse. Other studies show that parts of Turkey's crust aren't just stretching, they're dripping downward into the mantle. When dense chunks of crust get heavy enough, they peel off and sink like blobs of wax in a lava lamp. Scientists call it lithospheric dripping, and this process is basically Earth quietly losing pieces of itself. When that happens, the surface above weakens. The land rises, sinks, fractures, and rearranges. Earthquakes don't always need plates to slam together. Sometimes the ground fails because its support system melts away from below. That's why Turkey's geology now looks less like a solid slab and more like stretched taffy over a fire. Turkey isn't alone with the tectonic drama. Africa is unzipping itself so slowly that no human will ever wake up to a brand new ocean outside their window, yet fast enough that scientists can measure it happening right now. Deep beneath East Africa, the ground stretches and thins. Over millions of years, that constant stretch doesn't just rupture rocks, it rewrites geography. And it can literally create an ocean where solid land once stood. All of this focuses on something called the East African Rift System. This rift runs thousands of miles across places like Ethiopia, Kenya, Tanzania, and Mozambique, and it ranks among the largest rift zones on Earth. A rift zone is where the planet's crust is being pulled apart instead of being squished together. Africa doesn't just have a rift zone, but one of the most extreme versions anywhere, and it's been stretching for tens of millions of years, like a slow-motion disaster movie. And the continent isn't one solid piece anymore. It's splitting into two massive tectonic plates. The Nubian plate sits to the west, the Somalian plate to the east, and they're drifting apart at less than an inch per year, which sounds like a joke until you realize your fingernails grow at about the same speed. But just like in Turkey, this tiny movement adds up over millions of years. Back in 2018, photos of a massive rupture in Kenya caused chaos over the internet, and headlines panicked everyone with the news that Africa was splitting in half. The image looked intense, but it didn't mean the continent snapped overnight like a broken cookie. A much deeper process has been going on for about 25 million years already. And if we could jump another 5 or 10 million years into the future, we'd probably watch the crust stretch so thin that seawater finally rushes in and fills the gap. While Africa is tearing apart vertically, like a slow zipper, India could be splitting in a totally different way, horizontally into two giant layers, each about 60 miles thick, right as it crashes into Eurasia. And this collision is what gave us the Himalayas and the massive Tibetan plateau sitting behind them like a high-altitude backstage area. Everyone agrees on the basics. India has been creeping north for over 60 million years at about the speed your hair grows, slamming into Eurasia and forcing rock upward until it turned into the tallest mountains on Earth. What no one fully agreed on was how Tibet got so insanely high. Some scientists thought India was too buoyant to sink and just slid underneath Eurasia. Others imagined the plate buckling like a sheet of paper pushed into a wall. Then a third idea showed up and changed the vibe completely. This new theory says the Indian plate is delaminating, which means its top layer peels away and props up Tibet. At the same time, the heavier bottom layer sinks into the mantle, the hot semi-molten layer beneath Earth's crust. Scientists can't drill that deep to check, so they followed a clue instead: helium leaking from Tibetan hot springs. Helium-3 is incredibly rare and mostly comes from deep inside Earth, and helium-4 forms closer to the surface. When researchers measured gases from hundreds of springs, they found helium-3 leaking out in northern Tibet. It means that the mantle sits dangerously close to the surface there. Farther south, that signal disappears, so it most definitely means that the plate hasn't fully split yet. But we have earthquake patterns that line up with the same story, so it looks like India isn't just pushing mountains up. It's peeling itself apart from the inside while doing it. All these tectonic processes fit in well with the new massive global stress map. It shows where the planet is holding it together and where it's dangerously close to rupturing. Scientists built it from over 100,000 real stress measurements taken from boreholes, earthquakes, and field tests, which is more than double what we had less than a decade ago. Stress here means the invisible push and pull forces inside Earth's crust, the same forces that quietly load faults for years before one bad day turns into an earthquake. This map doesn't just help explain earthquakes, but also not to mess things up ourselves. If you drill a tunnel, inject carbon underground, or build a geothermal plant without knowing which way the rocks want to snap, you're basically poking a sleeping dragon. Engineers use this stress data to decide how to angle wells and tunnels so they don't accidentally cause failures. Basically, we're finally getting a live dashboard for Earth's breaking points, and that's a big deal when you live on the surface of a restless planet. For a long time, we treated continents like rigid boards floating on soup. Now they look more like stressed muscles, flexing, tearing, healing, and tearing again. It shows that the planet under your feet isn't finished. It's still under construction.
India could split horizontally into two parts as it runs into Eurasia. The movement of the Indian plate that includes most of modern South Asia is causing the Himalayas to grow. This process started around 60 million years ago when the plate first bumped into Eurasia. Scientists from the Netherlands have used the power of an AI simulator to see what this region will look like one day. The computer model showed that the Indian subcontinent will merge with the Horn of Africa in approximately 200 million years. The present-day cities of Mumbai and Mogadishu will become next-door neighbors. They will sit along the newly formed mountain chain scientists provisionally named the Somalaya. On the other side of this geological formation, Madagascar will connect with Sumatra, while Calcutta and the island of Mauritius will occupy the same region. Sri Lanka would cease to exist as it becomes part of the Indian mainland. Further to the north, scientists predict that the Himalayas are going to increase in height in the foreseeable future. As the Indian plate continues to mile northward, there will be major changes to the surrounding landscape. The present fault line will drift further south. Tens of thousands of years in the future, there might be no Nepal. The Himalayan range will have expanded sideways to fully engulf the mountainous country. And there may be way more earthquakes in this part of the world because of this movement. Most researchers agree the speed at which India is moving northward into Eurasia is barely a tenth of an inch every year. Some of them think this is happening because of the plate's buoyancy. It prevents the Indian plate from sinking into the mantle, which gives Tibet its elevated topography. Other scholars believe that the structure is buckling under the pressure. The process resembles what happens to a sheet of paper when you push it horizontally against a wall. As you apply more pressure to its edge, the sheet starts to rise in the middle. In the real world, this bulge would be the Tibetan Plateau. A recent theory gives us the third explanation for the process. Their paper still has to undergo peer review, but the findings are intriguing. The international team of researchers introduced a new concept, the delamination of the Indian plate. This term simply means the separation of layers in a material that is supposed to be bonded together. Think of a sandwich that has cheese and ham slices between two buns. Take one of those layers out of the sandwich, and you get delamination. In geological terms, this process involves the upper part of the plate peeling off and moving upwards.
In the case of the Indian plate, this is the section that supports Tibet's elevation. The lower section is denser, which causes it to sink into the mantle. Plate tectonics are, in this way, similar to a layered cake. Chefs place the spongy, denser layer at the bottom, so the heavier top doesn't crush it. Scientists developed their thesis by analyzing helium gases in water samples from the region's hot springs. Helium-3 is a rare isotope that shows that the mantle is close to the surface of the Earth. Researchers measured helium isotope ratios at 200 Tibetan springs. The pattern they saw shows how close the mantle is to the northern Tibetan surface. Further to the south, they found plenty of helium-4, another isotope, which means that the plate is intact. It forms a barrier that helium-3 cannot penetrate, except in one region near Bhutan, in the eastern part of the Himalayas. The seismic activity in the region is good proof that delamination, the sandwich theory, is all real here. And it shows us that the mantle is intruding from the eastern side of the plateau. This concept puts under question the old, established ideas about tectonic plate behavior. The scientists behind the study suspect that the unique shape of the Indian plate contributes to the delamination process. It's the thickest at the northernmost point and the thinnest on the sides. If it's all true, it will mean that the continental collisions have a more dynamic and complex nature than geologists previously believed. Scientists still don't have enough hard evidence to prove the correctness of the new theory, just hints. Drilling to depths of over 60 miles is mechanically impossible right now. Such excavations are necessary to be 100% sure that the delamination process is going on. With the right technology, we would be able to better understand the hazards associated with earthquakes in the Asia-Pacific region. It's home to the famous Ring of Fire, where 75% of Earth's volcanoes are located. 9 out of 10 all earthquakes take place here. The India-Australia-Capricorn tectonic plate beneath the Indian Ocean is also important for solving Earth's tectonic mysteries. The term geophysicists use for such locations is nascent plate boundary. These are plates where tectonic plates are just starting to pull apart or push against each other. They represent the initial stage of a full-fledged plate boundary. Such a geological transformation unfolds at a pace of barely 5% of a single inch per year. That's about as long as a strand of spaghetti is wide. This shouldn't worry us too much from today's perspective. The India-Australia-Capricorn plate is destined to split in half over the course of tens of millions of years. Scientists from France studied records of 2 earthquakes that happened in 2012 and concluded there must be a nascent boundary there. Earthquakes normally occur at places where 2 or more tectonic plates meet. But the tremors in the Indian Ocean happened in the middle of the plate. The scientists used sonar scanning to map out the seafloor and see what was really going on there. After further examination of the marine area off the coast of Western Australia, researchers found a complex network of 62 pull-apart basins along a fracture zone. The scientific data backed up the idea that the tectonic plate was slowly but surely breaking apart. It's another proof that the outer layer of our planet is dynamic, not static. In some cases, you don't have to be a scientist to notice these powerful underground forces. Massive crevices emerged almost overnight due to heavy rainfall in a seismically active region in rural Kenya, first in 2018 and then again in 2023. The local population named the biggest of them the Grand Canyon. These events were not one-time incidents, but signals from the East African Rift System, part of the Great Rift Valley. This huge geological phenomenon stretching from Jordan to Mozambique shows us the gradual splitting of the African continent into 2 subcontinents. You can find rift valleys all around the world as proof of how tectonic plate movements are changing the planet. The East African Rift shows the underlying dynamics of the Nubian and Somali plates. The Nubian plate bears most of Africa, and the smaller Somali plate cradles the Horn of Africa. The 2 are gradually moving away from one another which causes the formation of crevices within the rift valley. This process of continental rifting, going on at a rate slightly faster than the one in India, will eventually lead to the split of Africa into two continents. The whole process, which is about to happen in the next 10 to 50 million years, marks a significant geological event that reminds us of Earth's historical transformations. The last time our planet's geography changed so drastically was during the Jurassic period. The world map from the period looks recognizable, but the land masses were oddly positioned from the modern perspective. In the north, Eurasia was still loosely connected to North America, which was at the time called Laurasia. This landmass was slowly moving away from the supercontinent of Gondwana, further down south. It consisted of what we know today as Africa, South America, Australia, and Antarctica. At the time, the Indian plate was closer to Madagascar than to Eurasia, as it is today.
Now quick, how many continents are there on Earth? You'd probably say 7, I would. But honestly, this question doesn't have a right answer anymore. Technically, yes, Earth has 7 continents. But our geography books have been ignoring this whole part of the world. For years, scientists have been arguing that there's actually an 8th continent hiding out there, and it's called Zealandia. Turns out this lost continent isn't so lost anymore. A few years ago, researchers finally mapped out exactly where Zealandia is and how massive it really is. And that was a first, because Zealandia is nothing like the other continents. Think about it. Asia, Europe, Africa, you can spot them from space, or better yet, just look down at your feet. Right now, you are standing on a continent. But most people don't realize every continent on Earth has parts we can't step on, or even see. A lot of their land is hidden under the ocean, and those areas are tough to map or even explore. Now, imagine a continent that's 94% underwater. That'd be almost impossible to find, right? Well, that's Zealandia, a massive chunk of land located beneath the Pacific Ocean. And there's a reason for that. A long time ago, Zealandia was part of Gondwana, an ancient supercontinent that included South America, Africa, Antarctica, Australia, and parts of Asia. For millions of years, Gondwana held together until it started breaking apart about 200 million years ago. Its pieces slowly drifted in different directions, and one of them was Zealandia. At first, it was still connected to both Australia and Antarctica. But around 85 million years ago, Zealandia finally split off and began drifting on its own, becoming an isolated continent. Now, unlike Australia or Antarctica, Zealandia didn't stay on the surface for long. It sank. Today, only a small part of it sticks out above the ocean. That's mostly New Zealand, plus New Caledonia, and a few smaller Pacific islands. The rest is hidden under the sea. But hold on, how did Zealandia sink in the first place? For years, most experts thought Zealandia broke away in a process called a strike-slip breakup. That's when continents split apart along huge strike-slip fault zones, places where tectonic plates slide past each other side by side. But something about that theory never quite added up. After years of research, scientists think they have finally cracked the mystery. Turns out Zealandia's crust, or the outer shell of the continent, had been stretched thin. Yep, that's right. Instead of sliding sideways, like they once thought, the land was actually stretching and breaking. It's just like pulling a piece of dough until it gets so thin it finally tears. That's basically what happened to Zealandia. The land stretched so much it eventually snapped, and that happened because the tectonic plates beneath Zealandia were pulling apart, thinning the crust until it finally broke. And when it did, it cracked big time. The cracks were big enough for ocean water to rush in through the gaps, creating what we now know as the Tasman Sea. A few million years later, even more stretching left Zealandia's crust thinner and weaker. Eventually, it gave way, and huge parts of it sank beneath the waves, sealing its fate as a lost continent. But it wasn't all that lost. Experts had actually suspected its existence for almost 400 years, and the big clue was its unusual thickness. You see, Earth's crust comes in two main kinds. We've got continental crust and oceanic crust. They're both part of the planet's outer shell of solid rock, but there are some big differences between them. The continental crust is kind of like a Chicago deep dish pizza. It's thicker. The oceanic crust, on the other hand, is more like a New York slice, thinner. Now let's drop both slices into a tank of water and see what happens. Okay, let's just say the deep dish is lighter, so it floats. That's why continents sit above the ocean. The New York slice is heavier, so it sinks to the bottom of the tank. And that's why oceanic crust ends up lower, forming the ocean floor. There's another key difference too. Continental crust is made of lots of different types of rock, while oceanic crust is mostly basalt, that dark volcanic rock we get from eruptions. Knowing this, scientists used advanced technology to investigate the South Pacific. And what they found was surprising. Areas once thought to be ordinary ocean floor were actually basalt-free and much thicker than ocean crust should be. So wait, could our sunken New York-style pizza actually be a Chicago deep dish? Well, yeah. Even though Zealandia's crust is still thinner than other continents, it's way thicker than real oceanic crust, which means it's not just a patchwork of ocean floor and continental scraps. It's all continental crust, just a drowned version of it. In February 2017, scientists made the big announcement. Listen, everyone, Earth has 8 continents. Ta-da! But back then, they had no idea what Zealandia really looked like. There wasn't a map or anything, and that's probably why so many people still don't know it exists. Even inside the scientific community, not everyone was thrilled about calling it the 8th continent. Some people believe that the strange land at the bottom of the ocean was just a bunch of submerged fragments or microcontinents. Now here's the thing though, even before that big public announcement, an international team had already set sail on an expedition. They went near New Caledonia to collect seabed rock samples from North Zealandia, more precisely from Fairway Ridge in the Coral Sea. Fast forward 6 years, and those very samples unlocked a major discovery about Zealandia: its true size. The combination of rock dating methods, magnetic signatures, and tectonic mapping helped scientists define where Zealandia's boundaries lie. And they found that Zealandia has nearly 2 million square miles of landmass. To put that in perspective, that's about 20 times bigger than New Zealand. For many specialists, its size and completeness basically rule out the idea that Zealandia isn't a real continent. But why doesn't it feel official yet? I mean, we don't see it on maps, right? Well, that's because it's hard to get everyone to agree on calling it a continent. And the biggest reason people resist it so much might be pretty simple. It's just not convenient. You see, continents are generally identified by convention rather than by strict criteria. Depending on the perspective, people recognize 4, 5, 6, or 7 continents, because there's no such thing as a continent authority, and you are not going to see an international commission go on TV to name a new continent, or to make an official list of how many there are. Being almost entirely underwater doesn't help Zealandia's case. I mean, is it really fair to call it a continent, like Asia or Africa? Some people argue that if Zealandia qualifies, then other smaller blocks of continental crust, like the Cocos Islands or other microcontinents, could also make the list. So, how many more continents would we have to add to the list? See why it's not very convenient? Maybe it's safer to call Zealandia a submerged or sunken continent. That's more accurate. Although, to be fair, the true definition of a sunken continent is still kind of fuzzy. But honestly, I wouldn't worry too much about the official definition of Zealandia. What really matters is that fully mapping it is already a big deal. Just keep in mind that large parts of it remain unexplored. Scientists are confident that technologies like seismic imaging and deep-sea drilling will uncover even more about its structure and history. And just because Zealandia is mostly underwater doesn't make it any less of a geological marvel. This sunken landmass actually preserves clues about Earth's past that we might never see on continents above the surface. It might help scientists understand how continents shift as the plates move around. They also hope to find more clues about how drifting continents affect sea level, climate patterns, and the distribution of plants and animals. Each new discovery could sharpen our understanding of how Earth's surface reshapes itself. So, continent or not, Zealandia